Okay, good morning, everyone. So, before I'm going to make a brief uh, opening, so I'd like uh, to call a colleague from the central administration of the university to give you a welcome. So, Professor Yuri, please. So just one small comment. So we decided to make a very informal the open ceremony. So we are in a great family. So we hope that it's a standard in Latin America conference.
Thank you. Good morning, everybody. Bom dia. I'm here representing the rector of the university, Professor Paulo Vargas, and Professor Rony Pignaton, who is the vice rector. I'd like to welcome you to Espírito Santo, the state of Espírito Santo, the city of Vitória, and UFES, our university. My name is Yuri Leite. I'm the head of the international office, and our goal in the university is to help stimulate and facilitate the internationalization of the university. And one of the areas that where the university is more internationalized is research. So it's a pleasure to have you here from different parts of Brazil and different parts of the world. This is the 17th, right? Conference, I think the third in Brazil, right? And the first here in Espírito Santo, okay? I had to. I'm a professor in biological sciences, so when they invited me to talk here, I said, "What's the Mossbauer effect?" So I was like, I have to learn that before. So I look it up, and I figure it's a very important topic, and especially in physics and chemistry, but also has applications in biology. So at least I learned something new. I just want to welcome you. Make yourself comfortable. I hope you enjoy the university and the city, and I hope you have a great time and a productive event. Okay, thank you very much.
Thank you. Okay, thank you very much, Professor Yuri. So, as he said, I'm going to follow something that I wrote, because if I take the microphone, I can speak much more than should be. So, as I said in the beginning, good morning to my friends from the Mossbauer community. So, thank you so much to coming to Vitória and join us in the LACAME 2022. This is a meeting that we, from our group in Vitória, myself, José Rafael, Valberto, Carlos Larica, Tiago, and others, have worked very hard with our difficulties, as I said to Valdemar, so we have problems, economic and political as well at this moment. So the price of tickets in Brazil has increased, as in the world, quite a lot, and this makes a hard task for a student to join the conference. That's one of the big problems that we have. So our students, so if you look, we have two students from northeast of Brazil. We have some from the Maringá, so probably it's deep south of Brazil, and one in the north-south, for those that don't know the Brazilian map. And we hope that we can have a great week with a lot of scientific and social interaction. That's our big family, what we do. So we have to highlight that it is the first event that we have in Latin America with face-to-face features. So that's, we know that we had a lot of virtual meetings in Latin America and in the world as well. So in Brazil this year we had our national meeting virtually. So it was very nice because we keep our community on and work hard on that. So, but virtual conference, in my point of view, it was something that we had to keep the community together. And we did this in a very, very specific part of the time. But however, I don't like the virtual conference, because in the virtual conference, we don't have this interaction that we had in the beginning. And also the discussion, it's very, very roughly. So we never go deeper discussion. We hope that during the conference we can do this. So that's the point. And anyhow, we cannot cry for something that has already passed. So we have to look forward, and we have to work very hard to improve the things, and also we have to rethink about what we are going to do in the next few conferences that we are going to have. So for that, because we have this face-to-face conference, in-person conference, we have to thank very much for those colleagues that developed in a very short period of time the vaccine that allowed us to be here. So that's something very important. So I'm sure that the biotechnologists and scientists from biology, medicine, and so on, they work very hard, and we are very happy to them. And also we do our part of the job. You know, we do physics, we do science to help the people. So the second point that I would like to mention to some colleagues from abroad, so we have two of them invited. One has some health problem, and the other one has problem to get visa to come to Brazil. It's Nishkala from India. So we try with Brazilian embassy to get her visa, but so the bureaucracy, probably it's so big that we have not been allowed to have it. In the last week, we decided to make for these two person, so the talk by teleconference. So we hope that you can understand. We open this possibility because one has a health problem. So Professor Johan Litters, he cannot travel, and also Nishkala, because we have not been able to manage her visa. So we had 55 abstracts, submitted abstract, and we selected 52. So we have already 3 papers submitted to Hyperfine Interaction. We hope that more and more can send her paper or their paper to the conference. So we plan to keep the conference, the submission, at least for more 15 days. We're going to talk to Guido to see what he's going to do, if he accepts or not. Probably he is going to accept, because that's usually what we do in the conference. So we receive during the conference, and then we extend a little bit and we shift the time. So these abstracts are from Argentina, of course. We have 2 representatives, Professor Francisco Kiki, it's informal, no? And Gustavo. We have more from Colombia. We are very happy to have a lot of Colombians here, because they are going to organize the next LACAME'. And of course, from Brazil, Colombia, as I said, Germany, Kai, India, Nashkala, I don't know if she is online, and Peru. We have also a lot of Peruvian inscription, and also Professor Josh from the USA, and Grenache from France. And Grenache is a very well guy. He's look like a Latin American. He has been in most of our meetings, so it's same. We don't need to say Grenache is from France, because probably he's from Latin America as well. So we take, sorry. Yeah. To conclude, I'm going to be fast. I would like to take a minute of silence to 7 colleagues from Mosbara community that have been passed away this year. So I would like to to tell their names. It's Estavan Desi. He died July 17. Hirotoshi Sano, June 30. John Schiffer, June 6. Hans Fraudfelder, if I pronounce correct, I'm sorry, Germany, July 10. Philip Gutlich, September 9. Ekbach Bill, October 6. E Israel Novik, October 10. So this is for 1 minute for these guys. Okay, after this special moment, we would like to say that LACAME 2022 is formally open. We hope that you can feel at home in Vitória, at UF as well, and take advantage of the city. So once more, if you have any question, please do not hesitate and just ask us about the city. We have a very, very small city. It's very easy to walk about. And also, we have a very good beach board. So we can walk on the beach, we can relax during the afternoon of the conference. So stay here with us and have a nice weekend with a great time of interaction, scientific and also social, as I mentioned at the beginning. So now I would like to call Professor Juan from Peru. He's going to be the first chairman of the section. So if someone, since it's quite informal, the conference, if someone wants to say something, it's open to say. If not, we can say during the conference. Someone? No? Okay, Ganesh, please. Switch off their AC. Desliga o ar-condicionado. So, if we increase a little bit the temperature, or do you think that, okay, barulho, Rafinha, então tem que desligar por causa do barulho. The noise, okay. Okay, Juan, please, take your place. Please, yeah, please. Of course.
Hello. Okay, I just want to really thank you, Edson, and the guys from Vitória for the effort and making this happen. This is really a very tough moment in Brazil, and this is really not easy. And thank you very much for doing that. Okay, this is really important. Okay.
Welcome everyone. Can you hear me? Good morning. Can you hear me? So, our first speaker for today will be Professor Andrea Paesano Jr. The lecture title will be A Structural and Magnetic Study of Iron-57 Doped Nanostructure Monoxides. Please, we all give a strong clap to them. So we have 40 minutes for a lecture. Please, Professor.
Ladies and gentlemen, good morning. It's a great pleasure to be back to our conference, to give this talk to this friendly audience. I am Andrea Paesano Jr., and currently I'm a visiting professor at the Federal University of Rio Grande do Norte. But most of the experimental work I'm going to show you was developed at the university where I have my permanent position, which is the State University of Maringá in Paraná State. Well, the title of my talk is a structural and magnetic study of iron 57 doped nanostructured monoxides. But in fact, actually, this is a talk about pretty much about nanoparticles. As you know, nanoparticles are 0D materials with dimensions smaller than 100 nanometers, and they present the so-called size effects. Among them, we should cite broken bonds, crystalline disorder, spin canting, frustration disorder, surface anisotropy, which we can see in this idealized picture of a magnetic nanoparticle. It's usual to say that nanoparticles are composed by two regions called core and shell. They have a core and shell structure. It's important to pay attention to this point because this is the paradigm we are testing in our investigation. In nanoparticles, a surface plays a huge effect because decreasing the particle size, of course, there is an increase of the surface volume. There are several applications of nanoparticles, and I will say just a few: spintronics, catalysis, sensors, electrodes, biomedicine, and several others. That's why they deserve to be investigated. A special type of nanoparticles are those made with antiferromagnetic materials. Just to list the key features, they present large magnetic moments as established since by Niel for a long time. They may present a reduced Niel temperature. The core eventually have vacancies, and that's why this kind of nanoparticle may present magnetic moment. Often, they present a superparamagnetic behavior. The shell also may be magnetically and structurally disordered. They may present uncompensated spins, sometimes ferromagnetic clusters, and at low temperature, eventually a spin glass state. Well, the question is that the effects are not easily, the effect when we analyze the nanoparticles by magnetic measurements, is not easily to distinguish the effects of the core in separate of those from the shell. This is a difficult task. Even because eventually there is an exchange coupling between the core and the shell at a low temperature, which means that we may have exchange bias. The motivation for this investigation was to investigate the iron dope effect on some AFM compound nanoparticles. Of course, that it's interesting to dope with iron because we may apply Mossbauer spectroscopy together with other characterization techniques. Our investigation was about copper oxide, nickel oxide, and manganese oxide. Every oxides were doped with iron, but I'm going to show just due to time limitations today, I'm going to show you just the results about copper oxide and nickel oxide. The choice of these systems was based in different Niel temperatures. Copper is close to the room temperature. Nickel oxide is above. Manganese oxide is well below. Our synthesis process is a lyophilization process. we mix iron 57 acetate, homemade. We are able to prepare this acetate in our lab with the other metal acetate in water. And this aqueous solution is frozen at liquid temperature and then inserted in this part of this freeze dryer under vacuum for several hours. The resulting material is this fluffy powder, which is in the sequence retanelled for some hours, 2, 3, or 4, depending on the case, at this in this range of temperature and under nitrogen or argon atmospheres. We have characterized this material by several characterization techniques, electron microscopies, XPS, X-ray diffraction, magnetization techniques, and more extensively by Mossbauer spectroscopy. Starting with the iron, the copper, the doped copper oxide system, just to remember rapidly some bulk properties. The compound is monoclinic, is a semiconductor P-type, and the cationic site is very distortion. The compound presents two magnetic transitions. The first one, which is an AFM transition, is by 230 Kelvin. These micrographies show the nanoparticles. We measure the size of these nanoparticles using some statistics. And we can see here in this plot is the size of the nanoparticle as a function of the iron concentration. And we see that the undoped sample is almost out of the nanoscale. However, with a little bit of iron, the size decreases strongly. This picture shows us the diffraction results, X-ray diffraction results. Please note that the scale, the ordinate, was expressed in logarithm scale in order you better see if you have some extra peaks. If you make some careful inspection, you won't find no extra peaks, which means that all the samples are really monophasic. Well, at least in the resolution of the technique. Well, these diffractograms were obtained using synchronous radiation. We proceed to a Richenfeld analysis, and this plot shows us the crystallite size as a function also of the iron concentration. And we see here that this plot is more or less consistent with the earlier, because the crystallite size decrease under doping. These are the magnetization versus temperature curves obtained for the samples. This is a very unusual curve, but it's similar to others reported in literature. Here is the temperature, the Niel temperature. Well, after this intermediary situation, we have for these doped samples a more common looking for the curves. They were taken in the zero field cooling protocol and also in field cooling protocol. We see that this curve has a broad peak here. This is associated with, preliminarily, we can say that this is associated with some anti-parallel arrangement, probably some transition to the to the antiferromagnetic state in some regions of the sample or whatever other antiparallel arrangement. The field cooling curve shows this pattern, indicating that the sample is saturating the magnetization, probably saying that the nanoparticles have a liquid moment, a net magnetic moment. Here are the magnetization versus applied field curves taken at room temperature. You can see that here and here, there is no saturation. And for the higher fields, the behavior is linear, suggesting some paramagnetic fraction in the sample. But here we have a kind of S-shaped curve in the central part of the spectrum, and the same may be observed in these curves obtained at 10K. With the difference is that we have a robust hysteresis behavior here. We have also taken some loops under FC condition. And if you see here, the red was obtained under ZFC conditions, but the black curves were obtained in FC conditions. And a close inspection will show us that there is a shift of the black loop to the left, indicating that we have exchange bias in this system. Of course, if you have exchange bias, we have two magnetic components. Well, finally, the Mossbauer spectra, the so-expect-Hauer. We have measured for all samples. Here we see the Mossbauer spectra for two doped samples. The fit methodology was to use a discrete sextet, which is faintly visible even at room temperature, and also a hyperfine magnetic field distribution in the form of a histogram. It's a simple fitting, but was efficient. If you see here the sextet, the lines of the sextet are at the same energy, whatever the temperature. And the hyperfine field distribution is starts with something similar to a doublet and is splitting and becomes split at the lowest temperatures. Well, okay, it seems that Mossbauer also offers some evidence that we have two fractions in the sample. This situation of a sextet with the same strength, with the same magnitude, is typical for a classical magnetic relaxation when the magnetic field jumps up and down above some frequency. When we have a sextet beginning with enlarged lines, but when the jump frequencies is decreasing, the spectrum becomes a sharp sextet. Well, the same may be observed for this sample, and for these samples were the same. Plotting some values, plotting some values. Here we have the hyperfine field magnitude for all samples plotted against the temperature. You see here that there is no change in the value of the field. Regarding the distribution, you can see that the average average magnetic field increases under decreasing temperature. Our best explanation of this all phenomena is that the discrete sextet belongs to the shell of nanoparticle, and that the hyperfine field distribution is related to the core of the nanoparticles. It's interesting also to say that varying the temperature, the 60th area is constant. For example, for the 1% doped sample, the area of the 60th, it's always 11%. There is no changing of the area. So it clearly belongs to one fraction of the sample. And this fraction, in our opinion, is the shell. Summarizing the earlier results, we make this simple picture here, where we can see that close to room temperature, the core of the particle is in a paramagnetic state, and the shell also is in the SPM state. Reducing the temperature to the low temperature, the core becomes AFM ordered, and the shell becomes blocked at some below some temperature. This shell, okay, maybe there is some clusters, FM clusters here, but this is just a simplified picture of the system. Considering the Mossbauer relative areas, we obtained an estimation of the shell thickness for the 3 samples. We see here that, with the exception of this value, all the shells have more or less the same thickness. Okay. Sorry?
How much is the thickness? Sorry.
0.65, yeah, nanometers. 0.61. Okay, these values were obtained considering an homogeneous iron concentration. This is a hypothesis questionable, as we are going to see in the next presentation. Well, about the nickel oxide system, doped with iron, we have to say that the bulk nickel oxide crystallized with the cubic structure. It's very common to have a lot of cationic vacancies in the bulk compound. The cationic site is cubic, although some authors say that below the Niel temperature there is slightly some shift from the cubic symmetry. This is the magnetic structure of this P-type semiconductor, and I have to say that pure undoped copper oxide nanoparticles were extensively studied. There is a lot of results in literature. I choose some authors that, in my opinion, reported the best results, and some of the analysis I'm going to do are based in these papers here. Well, again, we taken some micrographies of the nanoparticles, and as before, underdoping the size of nanoparticles decrease from about 22 nanometers down to 15. The same diffraction analysis was conducted as before, and we didn't find no extra peaks. Apparently, the samples are really monophasic. Again, a Rich-Veld analysis gave us this plot here where we see that the nanoparticle, the crystallite size decreases with the doping level, as before. Okay, this is the curve, the magnetization versus temperature curve. We did this measurement. This is there is a lot of different results in literature. But some of the authors I cited before, they found similar curves to the nickel oxide. You see here there is in the ZFC protocol, this broad peak. Usually this is attributed to an SPM regime of the core. We have this, after this broad peak, we have another one, a sharper peak, which is in general attributed, but there are different opinions, different analyses. It's pretty much attributed to the shell, which could be in a spin glass state, but some authors say that this just is the reflex of some blocking temperature. This part here of intermediary temperature represent the progressive blocking of a system which has variation in the size of the core. That's why we have this so broad peak here. And the high temperature of this irreversibility here suggests some interparticle interactions in our system. Taking the same measurements for the doped samples, there is a big difference. That broad peak disappeared. There was a suppression of the peak. And this is a little mystery. We have some suggestion to explain this suppression. In our opinion, the peak was shifted for higher temperatures under the doping of iron, with iron. But this have to be better checked out. But that peak in low temperatures is here, and also here. There is a little shift, but this is not significant in our opinion. And here are the magnetization versus applied field curves. At room temperature, we have straight lines with a very weak of no hysteresis signal. And here at low temperature, we see clearly hysteretic behavior. At higher fields, there is some indicatives that the sample has an antiferromagnetic portion. But at low fields, there are some suggestions that we may have a ferromagnetic and or a spin glass portion of the sample. See here how robust is the hysteresis. Here are AC magnetization curves. The susceptibility was obtained as a function of the frequency. We have this set of curves here. You may observe that there is a small peak here, at 14.7K. There is no shift varying the frequency. But here there is a clear shift. You can see the shift observing this zoom of this peak. There is a shift of about 1.2 Kelvin. And in the doped sample, the curves are similar, but with a difference. First, the set of peaks are thinner and shifted to higher temperatures. You can see better in this zoom here. Here, 8 Kelvin, here 10 or 11 Kelvin. Well, some things, of course, happen with the iron, with the under iron doping. There is an empirical parameter frequently used in literature with this expression to classify if the transition is of the kind spin glass, if the system transits to a spin glass state, or if it's just a blocking of the superparamagnetic behavior. In general, to be a spin glass, this parameter must be between these two values. Our calculations show that for the undoped sample, this value is a little bit higher, whereas the value for the doped sample is in this range of numbers. So, at principle, we probably have below this temperature a spin glass state, much probably clusterized form. Well, the Mossberg spectra, this picture shows the Mossberg spectra taken for some samples, varying the temperature. The fit methodology we have used, we use a magnetic field distribution and a doublet in the temperatures for this spectra obtained at room temperature or near the room temperature. You can see the doublet here, but decreasing the temperature, we use a 2 sextet. You can see here, sextet 1, sextet 2 and 3, 1 and 2, but the doublet remains here. So again, this fitting methodology was simple, but it shows some self-consistency. We have again two components. Probably we can attribute to the one to the core and the other to the shell. This doublet, we understand that belongs to the spins, the iron spins at the very external part, very external surface of the nanoparticle. But the mystery remains. Who is who? Is the sextet one could be attributed to core, to the shell? Okay. Let's see what happens. Let's see what happens. My time is almost finished, isn't it, Charmaine?
5 minutes, yes.
5 minutes, okay. Well, the other sample shows the same systematic. At the lowest temperature, we have taken a Mossberg spectrum. There is no more doublet, but it's still 2 sextets. And at some times, we taken an XPS measurement. And, surprise, the iron concentration estimated was 70% cationic percentage, I mean. So this is very different for this sample of the 3% of iron. For us, it was a surprise. It means that the concentration of iron is not. There is probably a strong gradient of iron in the samples, in the nanoparticles. Well, I will leave this part. It's very interesting, but okay, I'm going to summarize the results. But before, let us see this interesting plot here. For 100 degrees, 100 Kelvin, the magnitude of the sextet 1 and the magnitude of the sextet 2 decrease with iron concentration. This is very unexpected. I never saw that. In general, you insert iron in the matrix and the magnitude of the field, at least when we are working with no magnetic matrix. But in this case, it was very unexpected. Well, this raises the idea that the more iron, there is a weakening of some magnetic interaction or something like that. The same occurs for 50 Kelvin. The sextet 1 decrease. This is different. It's a point out of the curve. Maybe this is important. I don't know. And the sextet 1 also decreases the magnitude. Analyzing the areas as a function of the concentration, you see here that the area of sextet 1 is more or less constant. It seems do not depend on the concentration, and the same occurs to the sextet 2. Summarizing these results, yes, we have, in our opinion, we have a core shell structure. Under doping, the nanoparticles decrease in the size, and there is a decrease in the magnitude of hyperfine magnetic field. The core, at a first view, the blocking temperature of these nanoparticles was shifted to higher temperature, much probably above the room temperature. On the shell, there is a undetermined nature of the peak by 50 Kelvin. We don't know if it was that peak found in the AC magnetization curves is due to a blocking, to a freezing, or whatever. And the sharp peak found at very low temperature. At temperature smaller than 10 Kelvin, really say us that we have a spin glass like below 10 K. Well, as I said at the beginning, all these results are very fresh and not completely understood. We have a lot of work to do. And to finish, I thank you very much for your attention.
Thank you very much, Professor Paesano. Now we have some questions from the conference attendants, please. Jean-Marc.
Thank you, Andrea. Could you show the slide where you were presenting the scanning electron microscopy, translucent microscopy?
Of the nickel oxide system? Copper.
Was slide 5 or 6 at the beginning? Yeah. So I am a bit skeptic on nanoparticles. Because you are
I could agree with you for this situation because, in fact, this is an average. You see here the distribution in size.
No, but
But this, are you saying about this?
the
Well,
problem is not the size.
yes, there is, I see that there is an agglomeration, but the particles were, see, this is 50 nanometers. This particle has 50 nanometers, more or less.
Yeah, I agree, but the problem is it the main contribution from the surface or from the interface? Because as you have an agglomeration, probably what you can say, and in the case of metallic system, you have grain boundaries. And this is probably related to synthesis. Because so you started with some iron 57 acetate. So it is also another question. What about the homogeny? And why the particles are agglomerated? It's a question.
Well, my opinion, hello. In my opinion, is because the shell, as I showed, has a magnetic moment. At least at low temperature, but not at room temperature, of course.
Up to now, I'm not speaking on magnetism. I'm speaking on what I see.
So is there a way to avoid the agglomeration through the synthesis process? Maybe changing the
no,
argon nitrogen
yeah,
ratio?
there are a lot of possibilities, but we didn't try to do that. Yes, I recognize that the, sorry, I have to return to the magnetization evidence. There are evidence for interparticle interactions. That's right. That's right. We see here. You are right. You see here. We see here, and we measure. There are magnetic evidence for that. Okay. No, it's a nice work to try a synthesis process in order to separate the nanoparticles. Yes, I agree.
It's a main question.
Yeah.
Now, when you are considering some particles, for example, 1% iron content, so 40 or 50 nanometers. So you have a layer of 4.6 nanometers. I do not understand because 4.6 nanometers for the thickness of the shell thickness. You can take it's too small. Could you hear me
Yeah.
before?
Yeah. I hear you.
Because typically, when you have some nanoparticles about 30 nanometers, because if you calculate the ratio of the surface or the volume of the shell of the total volume, it's less than 1%.
I
So I
understand
do
your
understand.
question. Yes. First of all, it was an estimation, but this estimation was done using the Mossbauer relative areas. In fact, if we
So what about the ratio of the two contribution by Mossbauer? Yeah, for example.
here.
Yeah, but
No, I take into account the Mossbauer relative areas and calculate the volume.
no, it's not possible.
No, considering with this
Because could you be back to the Mossbauer spectra?
with this
Yeah, okay.
hypothesis.
Could you be back to the Mossbauer spectra?
Yeah.
So you have one component is about 10-15%, the red one, compared to the other one.
See here,
Yeah, 10%, of course, yeah.
11%, 50, 20, 21. Yeah, this seem too much. But if the problem is that the volume is proportional to the radius at the third. This means a very thin layer. This is the calculation. This is the calculation.
See, next question from Professor Edson.
Uh,
Just one more question.
Dr. Grenache, we can, after the, to discuss a little bit.
The coffee break, please.
My question is, when you dope the copper or any oxide, so you have a reduction, and it seems that your distribution, the size distribution, get narrow. That's right?
Yes,
Okay.
that's right.
Okay. And then if you take the particles, you are assuming, in case of copper, you are assuming that the sharp cyst that it's associated to the shell contribution. Yeah. So can you go back again to the Mossbauer spectra? You take the sharp cyst and you associate with the shell contribution. Because for me, it's something very surprised, because at the surface, I would expect a much more broader component. So you are associating the sharp cyst to the shell contribution, and also the broad magnetic spectra you are associating with the core.
Yeah.
That means your core, you have a very broad distribution of particles.
Yes, yes. But remember that the shell, in our estimation, that we are going to check with Dr. Dr. Grenache after, but in our estimation, the shell has the same thickness.
You have assumed a spherical particle.
Yes,
Okay.
yes. This is a
And what
work
about
hypothesis.
what about the spin glass state? So the spin glass can come from the surface in case of nickel oxide, or it comes from the particle interaction, like a cluster
Are you
glass.
talking about the
Nickel oxide.
The nickel oxide.
Yeah.
Okay, what is your question?
No, my question is more or less like that. So you have assumed that you have a spin glass-like
Yes.
behavior.
Uh-huh.
So your spin glass-like behavior comes from the surface, or it comes from the
Yes.
interaction between the,
Yes.
the grains?
Yes,
It's like
comes from the surface. And I'm not being innovative. I'm not the first to say that.
Okay.
As I told you, part of my analysis was based on those analyses made by others in the past. And I agree with this idea. I mean,
Yeah, okay.
Okay,
Thank you.
one more question, please. We are on time.
Andrea, I was surprised with the with the contribution of the shell for the copper oxide. You attribute the shell a ferromagnetic state, right?
yes.
How do you know it is ferromagnetic state?
Well, this is because, firstly, because you have a field. The idea, we have a field jumping. Up and down. At low temperatures, these jumps stop, right? These jumps stop, and most probably this is an FM state. And also because, but let me try to answer to you. Also because we have another evidence, which was the exchange bias. Is an indicative. The core, in our opinion, at low temperature is an FM, blocked FM, 8 FM. What is the second, could be the second phase?
Yeah, because from Mossbauer you can say if it is ferro or antiferromagnetic, right? But you need another evidence from, I don't know, from magnetization, another technique to say if it is ferro or not.
Yes, but I believe that.
Just one small comment. Probably what you call ferromagnetic state is not the conventional ferromagnetic state.
Maybe a week.
You have a liquid.
Yeah, no, that's it.
fish at the surface,
That's it.
which
Yeah.
give you,
Yes, it's
for
not a.
example,
Yes.
a coefficient
Yes.
field, and then you have interaction.
My simplified picture showed that.
You have the grains, which may have
Yeah.
ferromagnetic state
Yeah.
with a state with a net magnetic state.
Dalbert,
That's probably.
Dalbert, Um, just a moment, Albert, please. See these FC curves? I cannot recognize any AFM contribution to that. Is it possible? No.
You have only a possibility, but now it's difficult.
Yes.
Is to apply external electric field with more power.
So you assume some evidence to construct your model. Okay, you have to check more, but at the state of art, our state of art is one.
That's okay. Well, thank you very much for the questions to the audience. Well, let's continue with our next talk. Thank you very much.
Thank you.
So welcome to Celio Marques, Dr. Celio Marques, for the next oral presentation. Please. So excellent presentation, many open subjects about nanotechnology and nanomagnetism. So we can let's discuss in the coffee break. So welcome to Celio Marques, Dr. Celio Marques, please, with the title Mossbauer Spectroscopy, Measuring Sense, a Model.
Problems here. I will try to present to you some of the conclusions of my doctoral work that I developed at CBPF with Professor Sérgio Duarte. The title of the work is Certain Neutrino Nucleus Scattering with Mossbauer Spectroscopy. I'm very grateful to Professor Edson, Professor Larica. In fact, this is my initial development was here at UFS, so I'm very grateful to be here today and for the thank you. So I will try to explain to you some of these conclusions of this work based on my reflections about the neutrino interaction with the nucleus. In fact, when the neutrino appears in science, this was only a hypothesis made by Pauli, and this particle has very mysterious behaviors until nowadays, and many of the phenomenology and interactions involved at neutrino physics are open now, and we came to the conclusion, because Mossbauer is a strong, precise technique, this technique could be show some of these behaviors, especially when the neutrino interacts with the nucleus. This was the main conclusion of our work. And the point is that when the neutrino scatters the nucleus, the main purpose we expect to observe is the recoil of the nucleus. But Mossbauer, exactly, the nucleus interacts with the neutrino, but Mossbauer nucleus don't are permitted to recoil. This is the essence of the technique of Mossbauer, and is exactly in this point we center our attention in developing our work, our thinking about the neutrino interaction with the nucleus. So the outlines are these two for this presentation. The neutrino at the standard model, which is the highest theory we have nowadays tested and presenting many successful results with the experiment and theory. And the standard model of physics nowadays has two second order, may I say, interactions or phenomenology called beyond standard model physics. In terms of theory of perturbation theory, these beyond standard model physics are second order contributions. And in fact, after we come to present these ideas at the community, many works have been emerging, discussing beyond standard model physics and Mossbauer spectroscopy. This was at some of last years after pandemic events we have recently. And so if we can see second order effects, so first order effect, with many more reasons we are capable to see. This is the principal defense we are made in connection with the Mossbauer spectroscopy. What the Mossbauer spectroscopy can say about the weak interactions, which are standard model interaction, the unification with the electromagnetic and weak decay of neutron, turns out the weak interactions, and what the Mossbauer spectroscopy are saying about the beyond standard model physics. These are the two outlines. First, I will try to situate to you with the some of the events we have in neutrino physics. In fact, when you expand the Lagrangian of the neutrino and matter interaction, nuclear interaction, pion interaction, etc., inside the standard model physics, we have six graphs, six interactions, which depends on the energy scale to appear. The most law interaction is this we are present to you, which are the interaction between neutrino and the nucleus. In fact, for the interaction turns out to be visible, we need the wavelength of the neutrino be comparable to the radius of the nucleus. So this sets the energy at low scale. Higher energy scale phenomena involving neutrino gives a spectrum of the particles, decaying, and this eventually this would be too visible at the Mossbauer spectrum. May I say it's possible, but our analysis sits at this low energy phenomena, because the recoil of the nucleus, the energy imparted to the neutrino at the nucleus, is so low that the recoil energy is comparable to the energy transition involving at the Mossbauer transition resonance, which is keV energy. The imparted energy that neutrino transfers to the nucleus situates the recoil of the nucleus which comes to appear, but don't appear because the Mossbauer nucleus is fixed. The condition is that the momentum after the interaction would be zero momentum, linear momentum at the nucleus. So this sits the nucleus fixed at the crystalline array, and so this energy, which is the recoil energy, which is imparted to the neutrinos, would be converted in some of the energy internal to the nucleus. Let's say the energy levels of the neutrons, let's say isomeric shifts or quadrupole splitting, and so on. So these four graphs is is not our interest here because the presence of high energy to the recoil sets the events more higher to the energy shifts of the Mossbauer transitions. But this 5-1 here, sorry, excuse me. This here is the highest energy phenomenon involving neutrino scatter with the nucleus, and eventually the neutrino is exchange some particle with the proton, and proton decays in many hadrons here. So he is the highest energy event we have interaction with neutrino, which is the energy scale JEV. And here is our coherent scattering with neutrino here, and the nucleus of mass number A here. The interaction is mediated by a Z0 photon, which is the partner of the Maxwell photon after the spontaneous symmetry breaking that comes at some scale of energy higher than this process, this particle decouples from the photon of Maxwell's equations, which is governed by the Maxwell's equations, and this photon is the massive photon that appears inside the electroweak theory. This is neutron photon, as we have the ordinary photon, but this has a large mass. For comparison, the mass of this photon is approximately twice the iron nucleus, for example. So this particle transfers the energy from the neutrino field to the nucleus field, to the nucleus particles. Especially this photon couples to the neutron content of the nucleus. So the neutron content of this nucleus is responsible to the carries the energy or may I say absorbs the energy imparted to the neutrino at this nucleus. This is the deep mass scattering, and this is a technical aspect of the interaction. This interaction was described by this Lagrangian in 1974 by Friedman. Firstly, Friedman showed that this Lagrangian gives this cross-section of this interaction, and this cross-section scales with energy square, and depends on the weak charge of the proton and the weak charge of the neutron, which is for some nucleus the number of neutrons we have at the specific nucleus. This term here, this parameter here, appears naturally inside the electroweak theory. This is called Weinberg angle. And when you compute this with the more recently parameters obtained by LHC and so on, this term gives 0. So the proton content of the nucleus don't see the neutrino field here. And only this term contributes with this coherent section, cross-section. This, as we saw, we have the low moment transference. This gives this constant here, because if you don't consider this condition, you have here the momentum of this is 0, but our consideration is that the wavelength of the neutrino is compared to the nucleus radius, so the momentum of the Z0 boson disappears from this interaction. Okay. Well, the typical cross-section we have in neutrino interactions are plotted here, and we see that the cross-section of the coherent neutrino nucleus is the highest one here. So this is especially interesting because if you try to observe the phenomena, you as higher you have the cross-section, as probably you observe the phenomena. So this phenomena has the more higher cross-section. If you count this graph, you have the neutrino electron, neutrino argônio nucleus, and so on. And the higher cross-section is that of the sense even. Here we have the principle of the Coney experiment, which is seated at the CBPF. This experiment used the CCD wafer, and the neutrino is supposed that the neutrino scatters with the silício nucleus, and eventually this scatters electrons, and these electrons and holes recombine, and you have photons, and so on. These photons gives pixels, and you amplify these pixels, and eventually you see the neutrino interaction of the nucleus. This technique presents some results interesting in recent years, but the linear of detection of the detector is reported to 40 electron volts, and the better observation of this experiment was made in 2007, 2017. I'm sorry. 2017. Thank you. And was made at the Coherent collaboration, which is a big collaboration at the United States. And this apparatus is a big crystal they developed to observe the neutrino interaction. And the linear is about 8 keV electron volts. It's extremely high. So the Mossbauer, we think we conclude this in our work, that this linear can be reduced considerably if you consider the Mossbauer technology, I say. This here is showing the beyond standard model physics and the standard model physics involving neutrino particle, and you have here this photon is supposed to exist dark Z photon. This is supposition. This is a second order phenomenon compared to this here associated with electroweak phenomena. And we have works that support that this interaction would be seen with the Mossbauer technique. This is the principal, may I say, good news we try to explain to you. Here you have the electroweak expected phenomena at the free space. And here we have the beyond standard model physics, which is parameterized by this parameter, which is connected to the density of the electrons at the material, for example. And this works sit this the conclusions in this direction, that the interaction of the Mossbauer nucleus surrounded by a density of the electrons, higher density of the electrons, you can see the beyond standard model neutrino interactions. This is the work we present in the literature 2018. Thank you. And this is the works at this year, 2011. No,
2020.
20.
Yes.
Thank you. This work here, and this other work, very interesting,
Yes.
to connect to Mossbauer spectroscopy. This is our model. This is a very technical developments to take this idea here, but in simple words, we have the surface characteristic of the nucleus perturbed by the neutrinos. The neutron especially is responsible to this, and we think that the ground state of the Mossbauer nucleus would be perturbed by the neutron interactions. Okay. And in fact, this idea appears at works after our works that present this, and connect to observation of second-order physics related to, in comparison to the standard model of physics. The Lagrangian is of this form. And so, in conclusion, we now are trying to explain, to modeling the sense even with quantum mechanics based on SUSE in connection with these colleagues here. Other intention we had discussing is propose an experiment together with others already installed in the world, in particular Corner or Corrigan, and with help to the LACAME's friends to think about the experiment, because we have many difficulties now to this connection that these two areas. Sorry. Finally, we have our works indicate that it's possible to search electric phenomena and Bayesian physics without, with the Mossbauer spectroscopy, and we need LACAME thinkers to search how.
Thank you very much, Dr. Celio. Please, a strong clap. So it's time for questions. We have 5 minutes. Any question?
Celio, can you comment a little bit, because you suppose that you have interaction between the neutrino and the nucleus. So that means you may change the nucleus radio, and then with this change you may change the isomer shift.
Yes.
The isomer shift.
Yes.
So do you expect to have, how much do you expect to have in change of the isomer shift before and after the neutrino interaction? Okay. So do you have an idea?
Yes. We have developed the idea that the volume of the nucleus changes with the radius. So when the nucleus scatters with the neutrino, the radius of the nucleus can vary with the energy, and this variation, you have the moments of this variation, and you can calculate with the expected value of this radius square minus square the mean square root of this radius with the neutron wave function. We have a difference in this radius, and you have this parameter of variation in nuclear volume reflects at the electron probability to are seen inside the nucleus.
Do you have an idea what this? How big is the change?
Yes, we made some. I'm sorry. So we made some of the estimations, and we have this result here. This is the probability to see the electron inside the nucleus, And this is the fraction variation of radius of the nucleus in function of the neutrino energy. This is a specific parameter associated with the potential you assume for the neutron interaction with the nucleus. Especially for this work, we consider the Wood-Saxon potential, which is common at nuclear physics, and we make this
Really small.
we arrive to this number here, nano-electron volts scale. Mossbauer, exactly.
Yeah, this is the
So-
order, the same order that was our
Sorry, I'm sorry.
transition. So we have time with one more question, please. Jean-Marc?
In your conclusion, you mentioned that there are some experiments in the world. Could you comment them?
The experiments at the world, yes. We have many collaborations. It's not studying the Mossbauer connection with the neutrino, but proposing that the Mossbauer see physics beyond a standard model. Our defense is that the standard model is more probabilistic. You have more probability to see standard model physics than beyond standard model physics. And the experimenters and people that search the quantum field theory and so on are proposing the Mossbauer window to see beyond standard model physics, which is more suppressed.
Sandro,
Just Gustavo Paskevich, you have more.
Yeah, the time scale of the weak interactions, especially those related to Z boson, is compared to that with the Maxwell's photon, which is gamma photon, for example, because the unification gives exactly this disconnection between these two fields. Exactly when you consider the refrigeration, the expanding universe, you decouple these two fields, the Maxwell fields and the zero field, for example. But the scale of the interaction with this Z0 boson is comparable to that of the gamma photon, for example. What is the big difference between photon and the Z0 photon? Is the cross-section, exactly. Because the photon cross-section is about of the order 17, minus 17 decades in terms of centimeters squared, for example. While the neutrino Z0 interaction is 13.9.
Okay.
In terms of centimeters square.
Thank you, Dr. Celio Marques, again. So we are on time. Please, Professor Dr. Kai. So our next speaker for oral presentation will be Dr. Kai Schlage with a title Not Collinear Spin Profiling in Single Magnetic Films via Oblique Incident Deposition. So welcome with a strong clap to Dr. Kai Schlage, please. Strong clap. So, let's start.
Yeah, thank you very much, Mr. Chairman, and good morning, everyone. First of all, I'd like to thank the organizers allowing me to give a presentation here. So it's my first international conference since 2.5 years, so first post-COVID conference. And then it's this really nice spot here in Victoria, so really cool. So I will speak about non-collinear spin profiling in thin films. That's what you see here. Which we use in this case is something that we apply in our group since a couple of years. It's called oblique incidence deposition, where we can induce unnatural easy access into thin films. And these collinear spin profiles, we detect or investigate them with nuclear forward scattering of synchrotron radiation. And actually all the experiments which I show you were measured at beamline ID18, at the nuclear resonance beamline at the ESRF, so European Synchrotron Radiation Facility in Grenoble in France. And at the beamline PO1 at Petra 3, so at my institute at DESY in Hamburg. And yeah, that's it. So that's the outline of my talk. First, I will give a short introduction into oblique incidence deposition. So what's the magnetic effect onto polycrystalline thin films? I will introduce our self-made sputter deposition chambers, which are optimized for this purpose. Then I will show two applications we are working on the last years. And in the second part of the presentation, I will then come to the main point, that's non-collinear spin profiling and single magnetic films. I will shortly repeat or give 2 slides to nuclear forward scattering of synchrotron radiation. And I will introduce a new approach for us, which we use to increase the depth sensitivity of this technique, to really screen the spiral as a function of depth. Yeah, and after the NFS results, I then come to the summary and then give over to the coffee break. So the effect of oblique incidence deposition on thin films that you can see on this slide. So on the upper right graph, you see a magnetization curve of a thin iron film, 5 nanometer thick, prepared in normal orientation or deposition normal orientation, so the conventional way. So the iron is soft magnetic and has no preferred magnetization axis, no easy axis, polycrystalline film. And its situation now drastically changes when you sputter deposit the same iron film 5 nanometer at oblique incidence. So in this case, as a polar deposition angle of 80 degrees. And now you see two remarkable effects. So first of all, you see that the iron somehow gets hard magnetic, so the coercive field, switching field is boosted by a factor of 50. And you see that the iron has now an easy axis, which is oriented perpendicular to the orientation of sputter deposition. So and this is due to a wavy surface profile, which is generated during deposition oblique incidence. And where the long-range dipolar interaction of the magnetic stray field lines on the surface cause then this hard magnetic state. And the cool thing is, so first of all, this works with practically all polycrystalline thin films, so even with amorphous cobalt iron boron. And you can even adjust the switching field, so the hardness of the film with the polar deposition angle and the thickness of the film. So if you decrease the deposition angle, you increase this wavy surface profile and the film gets more and more hard. So it's a really nice approach, and you see that magnetic properties of these OID films can be set precisely and flexibly. So we have the polar deposition angle, which determines the strength of the switching field, so the hardness of the film. And we have the azimuthal orientation of deposition, which determines the orientation of the easy axis. Yeah, so on this slide, I'd like to introduce the two sputter deposition chambers, which we set up especially for this purpose. It can be used for a variety of applications, but OID, the oblique incidence deposition, is a speciality. So you see we have a long tube. That's our chamber which we prepared 5 years ago with several slots, deposition slots. We can move a sample tower from source to source and then rotate the azimuthal and polar deposition angle to adjust the magnetic anisotropy in the thin film. Then due to a collaboration with the industry and some financial support from the government, we could set up a new chamber, which we recently finished, where we bring this now to a larger scale, so we can deposit this stuff now on 200 millimeter wafers. In addition, we can also go for 3D coating, so of 3-dimensional objects. That's not the topic of this talk, but I always like to show this video. So really nice sputter deposition chambers, which are then used for all the samples which you see in this talk. Okay, some applications of this OID technique. So actually this OID approach for single films known already a long time, but so far some people didn't really use it for multi-layer deposition. That's what we tested already 4 or 5 years ago. So it's the first proof of principle multi-layer structure which we produced. It's the iron-carbon multi-layer, whereas the iron layers are all deposited in oblique incidence at the polar deposition angle of 80 degrees, so they are hard magnetic, and every fourth layer is now deposited at a different azimuthal angle, so has a rotated easy axis. And to determine the depth profile, for sure we go for nuclear resonant reflectometry at our beamline in Hamburg. You see first of all the non-resonant reflectivity curve, so here's a critical angle where the X-ray penetrates into the stack, then you have the kissing fringes, then you have a small break peak due to the structural bilayer period. But if you now look to the nuclear resonant reflectivity curve, you have a similar curve with a break peak, but this additional side peaks, which is exactly due to the magnetic structure which we intended to go for. And from the fitting of these curves, we can now extract the magnetization depth profile, and we see that exactly we get what we wanted to have due to our deposition procedure. So it's so this ORD technique allows for new class of layered materials with averagely crossed magnetization axis and switching fields. So you can say layer number 14 should switch at a field of 40 millitesla. Easy axis should be oriented at 90 degrees, for example. So it's really nice. And you can make it in a similar manner with highest precision. So which is somewhere at least 2 degrees. That's the resolution limit of this technique. Okay, so this works for sure not for this scientific multi-layer system, but can be used also for sensor system, for example. So for example, for a TMR sensor, tunnel magnetoresistor sensor. So here you have 2 cobalt iron boron magnetic electrodes separated by a 1 nanometer thin MgO tunnel barrier. And the cool thing is now you can adjust the magnetic properties of both cobalt iron boron layers separately, introducing arbitrary easy axis switching fields, and this way create now sensors with completely different functionalities out of the same sensor material. Same tri-layer system, different deposition angles, new functionality, which is for sure quite nice. So what is now the topic of this talk today? It's a new approach, which we somehow started beginning of this year. We wanted to check if we can use this ORD technique to realize non-collinear spin profiles in single magnetic films. So far, all the magnetic properties of the films are due to a surface profile. So we have this wavy surface structure on the top, and we have a uniaxial magnetization. All the spins are looking in the same direction. The question is now if we can realize a non-collinear spin profile with this technique also. And actually the idea I got when I saw talk on an older publication where people predicted some special additional resonances. So due to a helical structure in 100 nanometer thick film, I thought that's also something what we could make with our technique in a much more simple way. So here it's coupled with iron platinum on the top and bottom side, quite complicated, and they predict this additional resonances. Yeah, but let's see. So the topic of this talk, or the goal of this talk, is to realize a spiral structure, and the proof of principle sample structure is shown here. It's a 10 nanometer thick iron film with a 90 degree crossing of the OID easy axis. So on the bottom side, it should have this wavy surface profile, which causes the easy axis along this direction. And the top part, a wavy surface profile, 90 degree orientated. And then due to relaxation, what should somehow create the spiral. That's what we want to go for. And that's the way we intended to realize this. So first we sputtered deposit now a carbon layer, because you cannot produce this wavy surface structure by itself. So we produce now first a carbon layer, deposit at 90 degree. We have this wavy surface profile. Now we sputter deposit 5 nanometer iron on top in normal incidence, so where the bottom part of the iron reproduces this wavy surface profile. And then we rotate our sample 90 degrees, sputter again iron at the polar angle of 80 degree, and we have now this wavy surface profile rotated 90 degree. So in principle, that's what we like to have. And from the magnetization curve, especially for the when we sweep the field parallel to the top easy axis, we see now there's a round chip magnetization curve, so a mixture of the easy and hard axis, which was for us the first hint that there could be some kind of spiral structure. But for sure, to detect this, we go for the height of the waves is around 1 nanometer, but it's it depends that it's maximum height of this waviness for very oblique angles. So, but for sure, to detect this, we go for nuclear resonance scattering. So that's why we're here. So just to remind you about nuclear forward scattering of synchrotron radiation. So we excite all the possible nuclear transitions with a short synchrotron pulse at the same time. We have a current re-emission in forward direction, which then causes a speed pattern, which we can detect with a fast photodiode, so with an APD, avalanche photodiode. And this allows us to determine the magnetic orientation relative to the photon beam. So it's a fingerprint of the magnetic structure of the sample. So that's how it looks like. So at Petra, we have a spacing of 192 nanoseconds. And then we detect the nuclear signal in between the pulses, so the nuclear de-excitation, to determine the magnetic orientation. You see now here, when the magnetization rotates relative to the photon direction, you see the change in the nuclear time spectra, which is highly, highly sensitive. But for sure, a question arises now, we have the technique which is sensitive to the magnetic orientation, but for sure we have a sample system with or hopefully with a distribution of magnetization, which we like to determine. So we will always get a mixture of the signal. And to solve this problem, as I said in the beginning, we go for a new approach. Okay, but that I know, it's isotope sensitive, sensitive to magnetic orientation, magnetization dynamics, background-free technique, and it's fast, and we work with a very small beam, the micrometer range. Okay, but to solve the problem with the depth sensitivity, we go a new approach. So we don't place our sample on a pure silicon wafer, but on a multi-layer structure. So standing wave field generator, and if we illuminate now this sample system at the break peak of this multi-layer structure, we create this standing wave field pattern with this very sharp waves and with a practically 100% contrast. So we can nicely select the part of the iron film which we like to investigate. So there are now two ways to move this wave up and down. So first of all, you can slightly move the incident angle. So to move this wave inside the thin film system which you want to investigate a little bit up or down. Or you place a wedge below your film of interest, and then you keep the incident angle fixed. So you have a fixed standing wave field, and then practically move your sample up and down by a lateral movement of your sample. It's again shown here. So we illuminate our sample system at the first break peak of the X-ray standing wave field multi-layer generator. We have the standing wave field, and then we have this wedge below. Moves the sample a little bit to the left and right, and this practically moves the sample system up and down, and we can measure on the top, bottom, center. Oh, I have to speed up. I have to say, so I have to speak faster. Yeah, just that's here the way where we make the X-ray standing wave field generators in our large chamber. Quite nice, excellent homogeneity, very small roughness, and due to the large size of the sample, where we use foreign sputter sources, aperture system, and a translational sample movement, so we always make 10, 20 samples in a row. It's really cool. You see one example, the electronic reflectivity of such a multi-layer structure. And that's now the final structure which we have here. That's our sample system where we expect the spiral, the multi-layer below, then here's the wedge, so we move the sample to the right and left. First, you see the electronic reflectivity. It's very similar to that what you can measure in the lab with an X-ray device. It's a little bit squeezed. You have a higher energy. Again, you have all the break peaks. Third break peak suppressed due to the ratio of the multi-layer structure. But now we come to the nuclear resonant reflectometry signal. What you see in blue, again, we have here this nice signal at the break peak positions. Here's the critical angle of the material, and here it's the first break peak. But first of all, you see we have a count rate of 10 kilohertz, so we can take a time spectra 2 to 3 seconds. So the fingerprint of the magnetic orientation. So it's really fast. Oh, we have to speed up. So now let's come to the results about the magnetic orientation. I start with a sample which is saturated along the easy axis, 70 millitesla. So all spins should look along the beam, should be oriented along the beam. Again, we have here our X-rays. Going into a sample system, we move the sample horizontally with a 50 micron beam, plus minus 7 millimeter. And now we can determine the depth profile. And you see here, all temp spectra look practically similar. That's because all the spins are oriented along the beam. You see the field distribution. So that's the area of the iron. And we can move this standing wave field pattern within the iron film up and down due to the lateral movement of the sample. And as I said, in this case, all the spins are oriented along the beam. Now this interesting situation, what happens when we remove the field? That's what we are looking for, if we can create a spiral. And here you see that we see now a drastic change in the nuclear time spectra for the different lateral position of the samples, so for the different depth position of the iron film. That are now the spectra which we took. In addition, we also took a time spectra at the critical angle, where you practically only illuminate the top part of the iron, just to be sure to cross-check. And then, that's what we get here. Indeed, we see a spiral structure. That are the angles which we extract for the 5-layer system. There's actually a new result here, where you see a smaller spacing. You see that all the spins on the bottom are fixed to the easy axis, which was introduced to the carbon layer, and then if you go more and more to the top, the magnetization rotates up to 90 degrees. The top part of the film is precisely oriented along the top easy axis. So it really works. And we have in this case a significantly stronger fixation of the magnetization due to the bottom wavy surface profile or interface profile. Okay, this I will switch. So we measured also additional configuration. But I will come back to the first slide what I showed. So this theory paper from 2015 where they said in principle this kind of helical structure should generate more FMR resonances. And that's what we also wanted to make, actually really new result from the last week. So we prepared, in this case, cobalt iron film, first a conventional one, deposited normal orientation. We have the typical V-shaped FMR pattern. And now we deposited two films with the same approach what I showed before, but the central part of the iron is now much thicker. So the overall thickness is 100 and 200 nanometer. Now let's see what we get. That are now the FMR measurement. And it really seems that we get some kind of periodic structure in the central part, but these results have to be checked again, especially this spiral structure has to be also remeasured at the beamline, or maybe even with polarized neutron reflectometry. But it's a strong hint that this approach to realize the spirals also works in much thicker films. So I forgot to say the easy axes are now crossed by 150 degrees. We once saturate the sample along the hard axle, and then everything spans out and we create a spiral. Okay, that's the summary then. So I introduced a new pathway to engineer, design new collinear spin structures in thin films. Thin film devices which can be applied for a variety of different materials. As I said, this ORD approach works for all polycrystalline films. So we achieved a stabilized spin spiral structure in the absence of an external magnetic field, a single magnetic material. So that's a big difference to other films. So we have a single magnetic film. We have no pinning layers on top and bottom, and we can freely adjust now the easy axis and the strength of the pinning in the layer itself. And I showed a successful application of this X-ray standing wave field generator approach for nuclear forward scattering, which allows for a direct measurement of the spin profile in thin films. And for sure, this works not only for the thick films. So last picture here, that's what we also measured in the same beam time. It's a 3 nanometer iron film sandwiched in different materials, in this case chromium and carbon. So we produce now an X-ray standing wave field generator with a smaller period. So the period has to be adjusted to the thickness of the film. And if we now screen the magnetization profiles through this 3 nanometer iron film, we see that the iron is magnetically stabilized on the bottom part next to the chromium. If we go up to the interface to the carbon, we see that the iron is practically non-magnetic. So we have a nice tool to really go for high depth selectivity screening of the spin structure of magnetization state in thin films. Okay, yeah, but at the end, I'd like to thank quite some people. So first of all, I'd like to thank Anjali Panchwani, which joined our team. So in the group of Professor Rolf Rölsberger 2 years ago, and is also working on this topic, help especially with data relation. I'd like to thank the people from Pier 1 at Petra 3 at DAISY and also at CSF, so Schumacher. That for sure also our engineer, person Lars Bocklager, wrote a new software for data relation, allows multiple fitting of this nuclear forward scattering, really cool. And for sure I also like to thank Ralf. So Ralf Rölsberger actually has now a second group, maybe someone of you know him. So first he was in Hamburg for a long time, but he became now a professor also in Jena, central part of Germany, so he has 2 groups. And last but not least, I would like to say, so if you're interested in to write a proposal for Petra 3, Pier 1, then feel free to contact me or Ilya Sergeyev. Okay, thanks a lot.
Thank you. So we have time for only one question, please. In any case, we lost the coffee break.
So all the magnetic moments are oriented within the plane. Or sometimes it could be all the magnetic moments are oriented within the plane, or is it possible to have some kind of canting?
It's a really good question. So for sure, this out of plane effect you usually get when if you grow the film thicker. So it starts at around 10 nanometer. But we have on the top part, put all these parameters out not to confuse the people. But we see that at the top interface we have a slight out of plane orientation. It's around, I think, 8 to 10 degrees. But I took everything out not to confuse the auditorium. But that's what we see, indeed. Mhm.
Is it due to the demagnetizing field?
It's again?
Is it due to the demagnetizing field?
I think it's for sure it's a demagnetization field, but it's transition from the wavy surface profile into something where you grow separated nanorocks which are oriented out of plane. So it's this transition region. And as I said, it starts usually at 10 to 12 nanometer, and we are in this region of 5 to 8, where somehow on the safe side, but you see already this first transition that you're not exactly in the plane anymore for the thicker films. So that's a limitation.
Thanks.
Separate the in-plane and out-of-plane contribution because, as you see, the roughness that you created, it shows that the shape anisotropy, you put the moment along to the, I don't know how to say this is, this top, this hill. So the magnetization should be that direction, and then I was expecting to have something a little bit canted
So
from
for
in-plane contribution.
So for the thin films, yeah, exactly in plane. So if you're, we're working a lot on the TMR sensor also for industry. So if you're in the region below 5 nanometer, you have 100% in-plane orientation, and they look all in the same direction. So that's what you, and for sure, NFS is extremely sensitive whenever you rotate out of the plane 5 degree.
One more question from Francisco.
Sorry, maybe I have lost your explanation before, I don't know. But what is the influence of the ratio between the thickness of the film and the height of the wave that you create?
So you have two possibilities to increase this wavy surface profile, whether you go to a more oblique angle. So the effect starts at 30, 40 degree and becomes really, really strong, 70, 80 degree, 85 is the maximum what we achieve. But for sure you can also grow the film thicker. So if you're at 60 degree and have a double thickness, you have an anisotropy which is similar to that what you had at 80. So it's a polar deposition angle which creates this wavy surface profile. And with increasing thickness of the film, also the amplitude increases.
Thank you.
Thank you very much. Again, Dr. Schlage.
Thanks, Edson, and Carlos, Rafael, all the people from UFES that made possible to have a LACAME conference again. And to see again many, many known faces, some unknown faces, no old faces, or there are no old faces here, as everybody knows. Okay. First of all, well, I would like to share with you a picture of my town, La Plata, where we work. And this is the Institute of Physics, where Gustavo and I work in La Plata, located in one of the campuses of the university. This is of our lab. As you see, there is a responsible team of which I form part, and leader, researcher, who is Gustavo Paskevich, who's really making a very impressive job in the laboratory. Fortunately, we have very good technicians at the institute, very well prepared, that support us very much. Well, I'm going to talk a little bit about nanoparticles and focus on the idea that these particles could be in the future applied in biomedicine. And it's normal to show a cartoon of the particles like this, meaning that these particles can perform a number of tasks in benefit of therapy or diagnosis, for instance. And I will focus in this possibility of the nanoparticles to become heaters, transducing magnetic energy into thermal energy. Okay, so first of all, I will make or remember some definitions. This property of the magnetic nanoparticles is usually evaluated in terms of two parameters. One parameter is SAR, which is the specific absorption rate is the power dissipated from the a radio frequency magnetic field per mass of the nanoparticles. And it could be measured calorimetrically by knowing the concentration of a colloid, for instance, and the rate of the temperature increase under the radiation with the radiofrequency field. And there's another parameter known as intrinsic loss power, which is the SAR divided by the product of the field frequency and the field amplitude to the square. This definition is understood, for instance, in terms of the linear response theory, which is the simplest way to treat this problem, in which the SAR has this expression, which depends also on the magnetic volume of the particles and on the spontaneous magnetization, and on the bifactor, which is written here. So ILP is an attempt to remove the extrinsic parameters of SAR, but it only does it partially, because it cannot remove the frequency factor which is inside the divide factor. Now, the idea in experimental therapy, which is named magnetic hyperthermia, is to locate these particles into malignant cells and produce the apoptosis or the necrosis of the cells by heating them up at temperatures of about 43 to 44 to 46 Celsius degrees. And of course, you can perform that with almost any kind of magnetic material if you increase sufficiently the frequency and the field amplitude But this cannot be done in any way, because there is a clinic discomfort limit, which is quite a subjective parameter, but it was proposed many years ago, decades ago, by Bersovich, a clinic discomfort limit in a work on the field with patients. And more recently, Dutz from the group of Hertz in Germany proposed a discomfort limit which is about 1 order of magnitude higher. But in any case, there is only a safe region where this principle can be applied if it's going to be applied for a clinical treatment with humans. Now, at the literature, we made a survey of these two parameters for nanoparticles made of iron oxide or coarser particles with a nuclei or core of iron and a shell of iron oxide, and also some particles which are pure iron. These particles here, from the group of Respo in France, where Medawi is the first author, really stand out from the rest of results in the literature, because both the specific absorption rate is very high for some of their particles, and also the ILP acquires very high values. In this work of Medawi et al., which is very nice work, they synthesized by the thermal decomposition route nanoparticles of different sizes, almost monodisperse. I mean, particles from 5 nanometers to about 30 nanometers, and they studied these particles very carefully, because they were just iron core particles with no coating, and they obtain these very nice results. Now, I'm going to show you a little bit what is the idea of our project. We want to have an iron core in order to have a strong magnetic response, as strong as possible. And we want nanoparticles with, which be reasonable biocompatible, so to an iron oxide shell, and also functionalize them in a simple way with a citrate function to make a stable colloids and to have a mean to stick some other functions to the particle, because the citrate function has 3 carboxylic units which can be used to that end. More or less, this is a summary of the project. And what is surrounded by the yellow line is what we have done so far, and we have explored part of the other part of the project. In this part of the project, we have prepared the magnetic cores, the iron cores, by a solid-state reaction. It's a highly energetic solid-state reaction, mechanically assisted. It's a method proposed by McCormick in Australia more than 20 years ago. It's a method where, well, I will talk a little bit on this method later. But this method utilizes an inner dispersant, which is sodium chloride, in order to avoid an explosive reaction, an excessive aggregation of the nanoparticles, and to reduce the dispersion of sizes. Therefore, you need to wash the products of the reaction, but because you have salts in your products. And then what we did was to add a magnetic oxide shell by chemical comprecipitation using the iron cores as seeds for the coprecipitation. And then to test the heating parameters are an ILP and the viability of one cell culture line. On the other hand, we are exploring the addition of an oxide hydroxide shell at room temperature by simply open air exposure of the cores. And we are exploring the kinetics and the type of result we obtained from these samples. Then we are also exploring the conversion of this hydroxide layer into a magnetic oxide layer, like an spinel. And in any case, we always end to having colloids which can be meant for biomedical applications or for environmental remediation applications, because the magnetic spinel oxides have been demonstrated to be very good for biomedical applications. But these oxide hydroxide materials that are produced at room temperature, like for instance, ferrihydrite or acaganite, have channels where they can capture contaminants, for instance. Okay, well, the mechanosynthesis, as I mentioned, consists on the obtention of the iron cores from anhydrous iron chloride with a, well, in principle it can be used an alkaline metal or ¿cómo se llama or magnesium, calcium, for instance, also, in order to remove the chloride from the iron. And as you see, the reaction releases a lot of heat, and then you have to use some amount of sodium chloride in order to perform the reaction. In our case, these proportions are meant in order to have 20% of the total mass of the final product be the iron cores. But this is a photo from the original paper of the group of McCormick in Australia with their results. Thank you.
The reactive was chloride, magnesium chloride, sulfates.
¿Cómo?
The precursors of magnesium can be chlorides or sulfates, salts in general.
The reactives are high purity, bought from some chemical company, iron chloride, anhydrous. It's very important that to be anhydrous in order not to put oxygen into the system. And these are, I'm sorry, these are magnetic magnesium shots, and this is 99.9% pure sodium chloride. Sodium chloride, yes. And well, we have tried this experiment in two types of mills, very small oscillatory mill where you can process about half a gram of material, a freeze pulvery set where you can scale about 16 times the production, and it would be possible, but we don't have to scale this process another 10 times. Yeah. So it is interesting because this method is in principle easily scalable, and you can produce quite large quantities of material for a laboratory scale. With this system, we can add a pressure sensor in order to monitor the advance of the reaction. Well, these are some of the first results that we obtained before the pandemic. Then we had to stop. Unfortunately, I would like to have more results today, but the project was stopped at that time. And the samples I am listed here. We were exploring the milling of time, the time milling, and also the mass ratio between the milling tools and the powder inside the vials. And here you see that initially when the process starts, there is a very slow increase of pressure inside the vials, and more or less about more than 1 hour, between 1 and 2 hours, there is a sudden increase of the pressure because of the self-sustained reaction, and then the reaction continues during at a slower pace during the next hours. Here is a mark for 6 hours, and this is a diagram for the advancement of the reaction, both with the milling time or with the intensity of milling. We have followed this essentially with Mosbauer spectroscopy. We have explored to put the amount of magnesium exactly the one required by the stoichiometry of the reaction, or less, in order to ensure that no magnesium is left as a metal in the final product. Another problem we found is the iron. We work most of the time inside a controlled atmosphere chamber, but even so, this reactive is very fond of oxygen. So even after a certain time of working, this reactive becomes partially oxidized, and then what you can see is some signal beyond the sextet of the alpha iron that is clearly visible in all the spectra shown in this transparency. But in any case, if you wash this material, the only thing that remains is the pattern of the alpha iron. It means that everything else which contains iron is in the form of salts, is soluble, and you can remove by washing. So in any case, you will always be sure to retrieve the iron cores. The only modification that washing produces with molecule water, we do this, is to produce a small layer of oxide in the surface of the cores. It's a very exothermic reaction also, the washing of the material. But this is very stable. Even after 2 months of exposing these particles to the atmosphere, the amount of oxide in the surface of the particle varies very little, for 10 to 12% more or less. No more than that. And the variation is faster at the very beginning of the structure. But you can, of course, if you let oxygen inside the milling vial during your experiment, you can increase dramatically the amount of oxide on the surface of the particles. But when I didn't emphasize in any way that the pattern of the alpha iron is very nice. It cannot be distinguished almost from the pattern of an alpha iron foil used for calibration. Here are the parameters we characterize this sextet. And this is because, well, the nanoparticles are large. We will see about 14 nanometers mean size. And but it tells us that there are no many defects in these particles. Jean-Marc?
I will ask the same question as for Andrea. You are using mechanosynthesis. You are obtaining nanoparticles or aggregates of nanoparticles.
Both. We are obtaining aggregates. I will show you that we have aggregates of nanoparticles. Yes. But we have to discuss this a little bit more later, okay? Okay, well, this is the some of the X-ray diffraction patterns. They are consistent with the size that I mentioned before. I'm sorry that we have lost most of the electron photos because of something. Well, I can show you. It was they were obtained right before the pandemic and the system which hold. They were not in the cloud, and they were lost, unfortunately. This is the shape of the magnetization curves on these large iron cores, and this shape here is very consistent with an arc tangent function, indicative of multi-domain material. This material can be stabilized, for instance, as I say, washing the product of the reaction, or keeping sealed the original mixture of iron cores and salts. If you leave this sample of iron and salts open to the environment, then rapidly transforms into oxide, hydroxide, and the magnetic response decreases dramatically. It is interesting, but it will be for another opportunity, that the shape of the of the magnetization curves also changes from the typical shape of a multi-domain particle to the shape of a single domain particle, and that the coercivity has a peak in between. So I think it's a very nice phenomenon to be studied in the near future. These iron cores were used as seeds for the co-precipitation of iron oxides, magnetic iron oxides, with adapter Massart root and stabilized with sodium citrate to make these colloids. These colloids have shown a very high stability. They present zeta potential of about 42 millivolts negative, almost constant in a wide range of pH, and they remain stable and with stable properties for more than 3 years so far. These pictures, well, as Jean-Marc said, it's not possible to say from this picture if the nanoparticles are individual or not. It looks like they are aggregated, and they. But anyway, it is possible to make some statistics and obtain a size distribution of the individual cores. Now, something happens during the co-precipitation, and it is that there is a drastic reduction of the size of the magnetic cores. It means the final particles have a mean size of 12 nanometer, and not 40 nanometers that was seen before. This is because the synthesis is made in an acid medium, and this acid medium dissolves partially the iron cores. And this is one of the reasons why we want to explore a different route. Well, these are Sachs experiments with, here you can see this is a Sachs pattern. This is a region corresponding to the nanometer scale, the size of the individual particles. And this region shows that aggregation occurs, because otherwise this part of the curve should be flat. And actually, or should tend to be flat, okay? With two different models, one model which allows for describing aggregation, the fitting is better. But in any case, the results from Sachs are quite consistent with the results from a high-resolution TEM, and have the advantage that you can sample a much larger quantity of material. This is a typical spectrum of the dried colloid of iron and iron oxide. Here, the pattern of iron is still visible here, and we have two other contributions, at least, a doublet here, the blue one, and a very relaxing pattern in magenta, with about 56% of the area corresponding to the alpha iron, and 44% of the area to the sum of the other two contributions. It is two contributions, both present the same isomer shift, and tentatively we ascribed these two contributions to the iron oxide, especially based in what we have observed from TM. Here from the film images are consistent with the interplanar distances of alpha iron, and the diffraction rings are consistent both with alpha iron and with the magnetic spinel iron oxide. We haven't seen anything else. If there is something else, should be in a minor quantity. So we interpret that these two contributions come from the same oxide, presumably from a shell of particles, and based on the isomer shift, it would be more closely to maghemite than to magnetite, their properties. Now, I will say something in regard to the question of Jean-Marc. On one side, we think that, well, we don't know exactly what is the degree of aggregation, and I'm going to show another result soon. But what we concluded is that the iron oxide is surrounded the iron cores because of, first, of the stability of the colloid. It means that the citrate function stuck very well to the material. It doesn't stick to iron, pure iron. It only sticks to iron oxide. So that should be, then the colloids are very stable, they remain stable. And then I will show you that, ¿cuánto? Yes, yes, it could be, of course. Yes.
The data of the dynamic light scattering value will be really important.
Yes.
The protocol to analyze correctly.
I will show you next that these aggregates are of the order of 100 nanometers. Yes, yes, that's right. But in principle, there should not be a large area of the surface of the material which is not covered with the oxide and then with the citrate function.
Yeah, and those aggregates are higher than 100 nanometers, of course.
Yeah, but even so, they remain stable in suspension for a long time. In fact, we are more interested in the application than in getting isolated nanoparticles. Well, this is a comparison of the response of the initial course, of the response of the colloid in the liquid state, which of course, well, not of course, but in this case is in thermal equilibrium and can be fitted very well with the Langevin type fit, typical of single domain nanoparticles which are in thermal equilibrium. And we have, of course, also tested the behavior as a function of the temperature. So simply for information, for the samples which were washed, the mass of the sample is simply the mass of the iron cores. The iron cores are weighted after washing, so we can calculate the magnetization. And in the case of the samples which have not been washed, then according to the stoichiometry of the reaction, 20% of the mass should be of the iron cores. We have performed UV-Vis measurements to estimate the total amount of iron in the samples, and the result is very, very close to this figure.
Francisco, sorry to interrupt. We have 5 minutes.
¿Terminó?
5 minutes.
5
Finish.
minutes, okay.
Yes.
And in the case of the colloids, of course, we measure the volume of the colloid that we measure, and knowing the concentration, we can estimate the mass of iron. That's the way we do. Well, from the different experiments performed, we have magnetization of the pure iron, of the unwashed iron cores, of the washed iron cores, and of the colloids here. And also the coercivity, which is more or less the same in the iron, in the cores which have been washed or not, and it is 0 in the case of the colloid because it's a liquid sample. From these results, we can estimate with a simple model, a core shell model. Of course, this model may not correspond to the reality. What is approximately the evolution of the sizes of core and shell. Okay, and this is what happens because of the chemical coprecipitation step. Okay, well, I will come back very rapidly to the performance of the material as a heater. We have done this calorimetrically. Well, I am presenting here again the results I presented at the very beginning of the talk, and the performance, the very good performance of Medawi's samples. These are our experiments. In the calorimeter, we obtained the time dependence of temperature. From there, we obtained the SAR and then the ILP. We obtained SAR values as large as 1200 watts per gram, depending on the degree of the concentration of the colloid. Could be from 700 to 1200 watts per gram. And ILP is extremely sensitive, especially at low excitation values, to the degree of dilution of the colloid. Here, the scale is the x-axis is in terms of the product of the frequency and the field amplitude, divided by the discomfort limit of Berzovich. And so this is the safe region we have defined before, and we will see that these particles, these colloids, have a very good behavior in this region. Here in red is one of our colloids, the one with 12 nanometers of particles, and well, we see here that at low excitation fields, it has a very good behavior, very much consistent with the colloid of Medawi, the 9 nanometers one. And our iron cores, the mean value of our iron cores could be more or less very much similar to this of Medawi here. And this colloid also behaves very much alike to the Medawi's one. We think that this is important because we can produce in a very much simpler way these materials and in much larger quantity. And our samples are surrounded by, or por lo menos our material is surrounded by the iron oxide, and Medawi's material is not. So in certain way, we have checked the result of Medawi because we obtain very much the same, and at the same time, we have found a route we think is easier, cheaper, and in a much larger scale. Well, nothing. I am going to try to finish in 2 minutes. So if we put here the effect of dilution, you see that this is the dilution original, which is 2.5 grams per liter. This is half. This is half of the half, and so forth. The ability to transduce the energy of the field into heat increases dramatically. And finally, well, we have performed some biological tests. For that purpose, the colloids were cleaned additionally, simply with water and magnetic separation 3 times. And then cells of the murine B16 melanoma cell line were cultured in a multi-well plate, about 10 to the 4 cells per well. And they were incubated with the colloid to these concentrations. From here, we took samples from them, observations, and to the MTT assay, which is the name of this substance that allows a colorimetric test. Well, this is the GM images of the cells incubated with the colloids, and the MTT results are quite good. They're about 80% of viability, which does not depend on the concentration, the 2 concentrations we have employed, which are the typical concentrations used for these tests, nor on the time the nanoparticles or the material remain in contact with the cells. So I'm going to finish here. These are the conclusions. I don't think it is going to be needed that I repeat the conclusions here now. Simply say that the other part of the project, which is underway now, is being explored, and it results, to me at least, quite interesting. The behavior of these iron cores as the oxidation reaction advances, because in the average, these cores should be reducing in size. We are not at the present in the situation to correlate time of oxidation to size of cores, because the situation is complex. But the shape of the magnetization curves changes very clearly from multi-domain type to single-domain type. These cycles can be deconvoluted in a ferromagnetic contribution and a linear contribution very easily, because the oxide hydroxide phases are paramagnetic at room temperature. And the coercivity of the ferromagnetic part shows that with the time increases and then decreases. So we think we are seeing an image of what happens with the nanoparticles as the size decreases, that the coercivity first increases while they are multi-domain, and then when they become single domain and another mechanisms of reversion of magnetization appear or take place, achieves the maximum and then decreases again as the particle becomes smaller and the magnetic energy needed to reverse the magnetization is smaller. Thank you very much. I hope.
Thank you very much, Francisco. Now we have time for questions.
Just one small question and comment. So you are talking about the iron core, that's the hard iron, and then you are proposed to be used to some treatment. So my point is, so usually when we work with nanoparticles, we always think about that to have biocompatibility. So do you believe that with metallic iron you have this possibility?
It's a possibility that is being explored by several groups, no? Like the Matisse group or some other groups have explored this possibility. And the rationality behind it is that you provide the biocompatibility with the shell. And then, in principle, once that is done, cells have a mean to get rid of the excess of iron in the cells. But I don't know. I'm not a specialist at that.
Just one comment relate to the Grenache, because when you saw your picture, you have this agglomerate, some agglomerates of the particles. So my point is, have you tried to put in the ultrasonic equipment?
Yes, of course.
To see if they can be separated or they are really like a nanocrystalline
Actually,
material?
functionalization with the citrate is performed under ultrasonic conditions. Now, I wanted to show, I didn't show before, these are the dynamic light scattering experiments showed at the aggregation. Almost a single peak of about at about 100 nanometers is it shows that there is aggregation, of course.
Yeah.
Yes.
It's not a question, it's a comment with respect to the question of Edson. So it seems to me that I have heard that when people was working on the targeting process for therapy, so the quantity of iron was not exceeded, was not toxic, was not so dangerous, because the human being can expulse iron. So the quantity, providing that they remain small, it's okay, no problem.
Yeah, you can. I think you cannot put something which is very reactive inside the organism. Okay, and finally, I forgot to put this final slide where the group is present. Diego Muraca, he's not anymore at the National Laboratory Nano in Campinas. He belongs now to the Institute of Physics, Clay Guataguin, and at the Unicamp. He asked me to change this, but I forgot.
It's important comment is to estimate the lethal dose concentration. Not only test two concentrations, maybe to use various concentration to estimate what is the.
You mean in the
50%.
biological tests?
Yeah, the lethal dose concentration.
Yes, of course, but there's an estimation of what is the amount of material that you are going to have during the application.
Yeah, and it's really important to plot it with the dynamic light scattering value. No?
You want to achieve that quantity in your tests.
Yeah.
So I think it doesn't matter to go to very high concentrations or very low concentration, but because they will not be of interest for the application.
Yes. Thank you very much again. Oh, one more question, please, from Professor Paesano.
Something, but I couldn't observe very well. What is the shape of your particles after milling?
Well, they are irregular, but we model them as spheres, of course, because they are not needles, they are not cubes, but they are clearly irregular. But
nearly spherical? Or
yes, nearly spherical. You cannot say that there is a dimension that clearly is larger than.
Maybe. Actually, there is.
During the milling, the atmosphere is. Well, once we did by mistake, okay, because the mill has a. I mean, when you close a mill, you go in the opposite sense that you do usually. But there is a tool which fixes the vial to the mill, which rotates in the opposite direction. So once it happened by mistake that when fixing the violin to the mill, the cap shifted a little bit and some oxygen entered, and then we had a lot of oxidation. But in otherwise, the seals are very good, and there's no problem with that.
One more final question, please.
Kiki, just a quick question. I didn't catch. How about the behavior of these particles against oxidation?
Well, the particles which remain with the salts, because the salts are extremely hygroscopic, they became a very fast process of oxidation. And the product is either a ferrohydride or acaganate. Actually, we use a paper by Barrero and Jean-Marc, where they characterize very well acaganate, and we saw that both the mean quadrupolar doublet and the isomer shift agree very well with them, and the diffraction lines also. I think that just one line we could not match with the lines of the paper of Barrero and Greneche. Yeah.
Thank you. Professor Juan? Final question?
Just one
Last
little question, because I didn't understand too well in your conclusions. You mentioned that the cells were internalized with the cortical iron oxide, and then remain viable to 80% at least during 22 hours. That's the last part is what I didn't understand quite. We are not familiar with that, no?
Well,
what
no,
that means.
I am not very familiar with that either, but I will tell you that what you do is you internalize the cells and you made the MTT test either 6 hours after, and in this case, okay, after the internalization, or 22 hours after the internalization. And depending on the color of the test, you can say what is the percentage of viability in the culture. You compare with the control, with a culture which has been done under standard conditions with no nanoparticles, and this is the 100% for you.
And what is the equal situation? Is that very good?
Well, according to the group of biologists with whom we collaborate, the result was good. It was quite good or very good. It was what they have their opinion.
So, thank you very much. I invite you now to Dr. Joshua Telser.
So just one small question, small point. So after Josh, we are going to stop because tomorrow it will be a free place, and then I ask Julian to give his talk tomorrow. That will be fine because it's already too late. We have to go to the lunch.
So the title of the next presentation will be 187th Osmium-Mosbauer investigation of osmium coordination complexes using synchrotron radiation. So, sorry. But I can mention that there are two important reviews from Gupta, from the disadvantages and advantages of preparation of nanoparticles from 2005, I think, biomaterials, and the protein effect formation also. No? It's very review interesting. Explain.
Okay, I hope I won't delay us too much. It's a pleasure to be here. This is my first Mosbauer conference, and so bear with me. I'm not an expert in the area, although I've worked with people that do iron Mosbauer spectroscopy quite a bit. That's my school. That's our new logo. And so the people that I've been working with, they're also not involved in Mossbauer spectroscopy, but I persuaded them to become interested in it, and that's mainly Professor Vladimir Aryan at the University of Vienna, Uni Wien, and his former student, Gabriel Büchel, who is from Liechtenstein. That's the Liechtenstein flag. And he's got his own business in Liechtenstein, but is still actively involved in this project. And then the people that actually, Sasha Chumakov has already been mentioned at ESRF in Grenoble. And the person, though, that I've worked with more is Dimitrios Bessas, who's from Greece, but also in Grenoble. And I don't remember. No, yes. And Sasha wanted me to mention the person who was the creator of the beamline that we're using, which is Dr. Rudolf Ruffler. And you can't read this, but it says that he won the IBAME, or however you pronounce it, award a few years ago for the application of synchrotron radiation to Mossbauer spectroscopy, which probably everybody here knows, but especially in the current environment of source difficulty, which we can discuss later, but I need not get into. It's really even more crucial now is the ability to do this important measurement with synchrotron radiation. So anyway, and then I also have to mention, I'm talking about osmium, but I came into that through ruthenium, and I had a collaboration with a really wonderful person that I don't know if he's known to people here, even from Brazil, Professor Douglas Wagner Franco, and that's his former student, Maicon, at the USP in San Carlos. And unfortunately, he passed away a few years ago, and you probably can't read this, but they recently dedicated the chemistry building at USP San Carlos in his name. He was a really great person and is partly responsible for my being in ruthenium chemistry to some extent. Anyway, another person that was involved in ruthenium was my thesis advisor, Russ Drago, a very important coordination chemist back in the day. And you can see these papers are from a long time ago, but they're on ruthenium compounds. We don't need to discuss them. But a very famous compound in inorganic chemistry is this one, the Kreutz-Taube complex, which is Henry Taube, the Nobel Prize winner that hopefully everyone should have heard of. But anyway, it's a very important system in terms of electron delocalization and was connected to the Nobel Prize also for Rudolf Marques about electron transfer theory. But anyway, so my advisor, Russ Drago, he worked on these as well, although I wasn't directly involved. These papers were from a little bit, somewhat before my time. Anyway, I should also add, I don't know if Dave Hendrickson's name is familiar to anyone here, but he did not do any Mossbauer in this particular paper here, but he did a lot of Mossbauer spectroscopy that in important applications of coordination chemistry at the University of Illinois years ago. So anyway, another technique, or the technique that I'm most familiar with, is not Mossbauer, but is paramagnetic resonance, mainly electron paramagnetic resonance, but also nuclear paramagnetic resonance or paramagnetic NMR. And I currently collaborate with Professor Brian Hoffman at Northwestern, and Pete Doan was in graduate school with me and now also works with Professor Hoffman. And so this is, in this paper here, in the whole historical connection, Mike Clark was a Henry Taube student. So it's all kind of one connected thing here. And they're doing EPR spectroscopy and NMR spectroscopy. These are paramagnetically shifted NMR spectra of a ruthenium amine compound that's related to the Kreutz-Taube complex, but the interest in these was a more practical one by Mike Clark, and that was anti-cancer drugs. Many of you probably know about the use of platinum complexes in cancer therapy. There's several clinically used drugs out there, and so there's been an interest in extending to other metals in the periodic table nearby to platinum, and that includes ruthenium, osmium, and others, but in particular ruthenium. So this was one, although it hasn't led to it. But what I'll get to is the compounds of interest that we're using Mossbauer on, which are anti-cancer related. More relevant to the people here is the work of Friedrich Wagner in Munich, or I guess it's Garching, in this paper, which is also on the Kreuz-Tauby, well, you can read the title, the Kreuz-Tauby complex revisited, and a lot of very leading people involved, but in particular, and this was something, this is at the time I was in graduate school, and I was quite fascinated by this work. As you can see, it's now almost 40 years later that I'm finally doing something about it, but Wagner used ruthenium-99 Mossbauer, which, you know, right below iron, but not so popular, and the source is this rhodium-99, and that was prepared in Garching, and they were able to do these experiments, but it's no longer possible, and maybe some of the people here would know, but my inquiries have led to the realization that ruthenium-99 Mossbauer is currently effectively impossible, even with synchrotron radiation. But anyway, here's some Mossbauer spectra, not mine, but of these types of complexes. You can see they look like Mossbauer, and that's about all I want to say about it. Another group, Greenwood in England, did some very nice work a little bit earlier, in fact. So that was the ruthenium Mossbauer aspect. And as I said, I really wanted to do this for a long time, but it seems to be impossible. However, there's also osmium right below, of course, ruthenium, which is below iron in group 8. And here's Wagner again in this paper that has really not gotten much notice, probably because of the difficulty in doing osmium Mossbauer, but it's a very, very thorough study. You can see the huge number of complexes. These are all molecular complexes. We've been hearing about solid state and materials. I'm coming from the molecular coordination chemistry direction, so there's no nanoparticles, there's no thin films, no materials. These are just ordinary inorganic compounds, but they looked at an enormous number of them and fully characterized them by Mossbauer, the parameters you can see here, quadrupole, isomer shift, all that sort of stuff. And this, I should point out, you probably can't read that, but this is osmium-189, which is reasonably abundant, 16%, and so the difficulty was the source, which they could prepare in Garching, but the abundance is enough that, you know, you can get spectra even for molecular compounds such as these. Here's the source is iridium-189. And it's not very convenient, but they were able to do it. I mean, excuse me, my impression is that Wagner was pretty much able to do everything with Mossbauer in those days. And this paper has only 12 citations, even though it's really the definitive osmium Mossbauer paper out there, but I guess, you know, that tells you how it is. Anyway, so what about the systems that we're looking at? As I said, this slide shows ruthenium, but pretty much, you know, there's an analog between every ruthenium and every osmium compound. They're, of course, not identical, but there's a pretty strong correspondence, and I didn't bother changing the slide from ruthenium to osmium, and it was relevant in terms of the studies we've been doing, or really Vladimir Aryan has been doing mainly on ruthenium. And so there's these two classes of complexes. One is related to the Kreuz-Tauby, and that has the equatorial amine ligands, the NH3 ligands, and that was what Mike Clark looked at, and those have not really worked out at all in terms of the anti-cancer application, even though if you're familiar with the platinum compound that's clinically used, that's a 4-coordinate compound, but with 2 amines on it in the original one. So this was a direct logical extension, but it's not worked out. This type of complex here, which is anionic as opposed to cationic with 4 equatorial chlorides rather than amines, is the one that people, or this class is what people are looking at for the anti-cancer drug treatment. And this is just some synthesis stuff that we don't need to talk about. So that's in clinical trials, although I should add that the application has been going on for many years now, and I have no idea whether it will really work out in the end, but you know, these things take a while. And as I said, the other kind has not. Okay, so in terms of the applications, there are two of that chloride type of compounds that are in clinical trials. One is from an Italian group, here is Italy, and it has a ligand that can vary, which is a imidazole type ligand, and then it has DMSO, dimethyl sulfoxide, at the other axial position. And then there's a very closely related one. You know, that's kind of how it is with drugs. I wouldn't call this the Me Too situation, but you know, they're very similar complexes that were developed in parallel by two extremely competitive groups with each other. And so this is the Austrian compound. Bernhard Kepler and also Vladimir Aryan, all in Vienna, are working on it. And this one, so that's the Austrian one. It's interesting, and it's certainly not something I can explain, but they have different apparent clinical or medical, whatever you want to call it, applications. And so it may be that both of them might work. So it's, you know, a winner, everybody wins situation, including cancer patients. That's certainly what we're hoping for. Okay, anyway, so the forms of these compounds that are administered are, this is getting to what my knowledge is that they're ruthenium or osmium-3, so that's paramagnetic, and this is just an orbital diagram. I won't spend too much time on it, but you have one unpaired electron, and then EPR spectroscopy is very sensitive to studying it. This is a very nice review article by the late Phil Rieger. And the idea here, I won't need to get into it, but the G values that one gets from the EPR spectra are very sensitive to the coordination environment. So EPR is a very good technique, and I can say that objectively. This is just a slide I made of the same type of behavior where the G value can vary depending on what kind of orbital the unpaired electron is in. Okay, and then this is just a final slide about that. Again, I don't want to spend much time on this. It was Bruce McGarvey in Windsor, Ontario, that whose work I've followed on in terms of being a little bit more quantitative about the analysis from this. And I should just mention, you know, in terms of the connections, one of the other things that Bruce McGarvey worked on was spin crossover compounds, and he worked quite a bit with Philip Güttlich, who, as Edson mentioned, passed away recently, so there was a lot of connection between the EPR and Nussbauer in terms of analyzing iron, you know, regular iron Nussbauer on spin crossover complexes. So again, everything is sort of connected in various ways. Okay, so these are the compounds that we're thinking about here. These again are all ruthenium, but there's osmium analogs for most of them from the group of Aryan and Kepler in Vienna. So again, lots of inorganic and organic chemistry here, but you know, you can see all these sorts of things. And you know, if you think about drug design, which maybe isn't something that we think about a lot, although we just heard a very interesting talk about, you know, medical applications of not molecules but nanoparticles. But you know, you're trying to make potentially small variations and hope that something works, because it's really hard to predict. Anyway, so then here's some of the osmium compounds that we're talking about for doing Nussbauer. And just one thing to mention, and this is something that we want to probe with Nussbauer, is the different oxidation states, because as I mentioned about the osmium-3 or ruthenium-3 being the main form, but with osmium-4 is also relatively stable, and so you know, we can sort of learn, I hope, about electronic structure from Nussbauer spectroscopy in addition to the other techniques. And then there's also, of course, the reduced form, reduced from 3, the osmium-2 and ruthenium-2, and those may be relevant, particularly in, you know, in the medical aspects I don't want to get into, but the tumor environment might be more reducing, more, you know, less oxygen, you know, who knows, there's various theories about that. And so this paper here I'm just mentioning is where osmium analogs were made and paving the way, blah, blah, blah. So that you know, in other words, just making the osmium analogs for the ruthenium anti-cancer drugs. Okay, so now finally we get to the thing that maybe is more familiar to people here. There's Dimitrios. And let's see, now I don't remember how these beamline names all run together. If this is the one that Kai Schlage, did you mention, was it ID 18? Yeah, okay. When you showed the number, I thought, oh, is that the right one? The numbers are all similar. Anyway, so Kai could explain this a hell of a lot better than I possibly could. This whole project, as Dr. Sanchez mentioned in his area, I mean, we've all been affected by the pandemic. So, travel for me and even access for the people in Austria to the beamline, everything's been tremendously limited, as everyone knows. But hopefully we're finally getting going again. So this is just a picture of this of the beamline that I just stole from their website. And don't ask me to explain it, but you could ask Kai to. Although this is at ESRF in Grenoble, not Daisy in Hamburg. Okay, so then there has been one paper out there with Dimitrios Besas as the first author, and Ilya Sergeyev. His name seems to vary in spelling, but anyway, and Sasha Alexander Chumarkov, Rudolf Ruffer, Volker Schünemann. I don't know if he's known to people here. He's in Kaiserslautern, Germany, and a very active Nussbauer spectroscopist who's doing some very interesting, I believe, dysprosium. I don't remember the isotope number, but dysprosium and other F element Nussbauer related to molecular magnets. So a plug for him. And then Peter Sadler is actually somebody, kind of a competitor of the Austrian group in terms of being in the metals and medicine in England. And Raphael Herrmann maybe is known to people also here from Oak Ridge. So the upshot of it is, I'm not going to read the abstract, but it says viability of nuclear resonance scattering is a reliable method to study electronic, magnetic, and elastic. Elastic is not something I'm so interested in. Properties of osmium compounds, including osmium organometallics. That's another class of anti-cancer potential drugs that Peter Sadler is involved in. So, when you see something like this, you think, hey, this is really something that we should be trying as well. Now, of course, they were using elemental osmium, which, it's quite a step to the complexes. But what Vladimir was able to get from some Russian sources that probably not available now, or who knows what the story is, but in any case, he was able to get osmium-187 metal, and very carefully, they're very good in synthesis, prepare a number of osmium-enriched compounds, very highly enriched. Gabrielle also was doing that. And so back in July, with the heavy COVID restrictions still in place, Dimitrios is already there. Gabrielle and Vladimir were able to go to Grenoble and participate in the experiments that Dimitrios was doing. And I watched a little bit, and I took a screenshot. And don't ask me to explain this, but it hopefully shows that some actual data is being recorded on osmium Nussbauer from just over a year ago. And you can't read this, but this is what I discovered when I was making this slide. This is something from my school about, COVID, this and that, and, it's all this COVID stuff. And here's the Zoom thing. It's like all the pandemic coming back to me here, just looking at my screenshot. Okay, so we looked at a number of compounds. Unfortunately, with the current beam time period that I was describing here, it wasn't enough to complete the project, but hopefully we'll get another one. We missed one of the calls for beam time, but hopefully there'll be one coming up soon, and that should be enough to complete it. But we did, or I should say, they got enough results on one osmium compound, which is not directly connected to the anti-cancer drugs. It's sort of more of a proof of principle, and it's this high oxidation state compound, osmium-6 is the oxidation state. And so it's not one of the drug candidates, but one of the nice things about it was that in terms of the mass percent of osmium, it's quite high. Osmium, of course, is pretty massive, but, when you have all that organic shrubbery around, which we have to have, that really cuts down, your active ingredient, and this has only some oxygen, so it's potassium also, but it's a relatively more bang for your buck, as we would say, in terms of the osmium. And so here's some data that's been worked up from it. So this is measured just at room temperature. I don't know this program, but it fits that, and able to get the quadrupole splitting, and the function here is, it's less that it was, I won't bother going back, but it was like 0.9 something, this recoilless fraction for the osmium metal. But here we're talking about an isolate, well, it's not completely isolated, it's got bridging, but it's still quite different from a metal in terms of the intermolecular interactions. So that's our first one, and
Just 2
then,
minutes, please.
oh, how much?
2 minutes.
Okay, that's fine, I'm almost done. And so Vladimir's friend who's also from Moldova, Liviu Cibotaru, may not be known to people here, but he's a very major person in theory of particularly molecular magnetism, which this is not exactly, but he's at KU Leuven in Belgium, and his co-workers, another Liviu and his postdoc, Jishuo Huang, doing some calculations on this, and there's sort of another direction of this work, not just the Mossbauer experimental, but to have theory, well, I should say to have experimental information from Mossbauer and other techniques such as EPR is important, because the 5D metals such as osmium are really a computational challenge. All the heavy, obviously the heavier you go, the tougher it gets with all the relativistic effects, and that's something that Liviu is interested in. So even though it's not an F element, it kind of persuaded him, oh, it's like an F element, it's just an F14 element, but whatever, it's still got a lot of electrons and worth calculating. So they're doing some calculations, and hopefully we'll be able to get a better understanding of what the Mossbauer parameters that we're going to get. So I'll skip the conclusions here to save time. As Professor Sanchez said, you don't need to read these, but here they are. But I also wanted to have one final slide after the conclusions, which is another direction. There's Ilya. Here I'm spelling his name without a U. I don't know which is correct, maybe, who knows. And then someone I met relatively recently, Tom Tietz at the University of Houston in Texas. And this is for doing iridium Mossbauer, so over to the right one in the periodic table. And the nice thing about this stuff, thank God, we don't have to get some crazy mysterious sources. This is, the way God made it, so to speak. 67% abundant is iridium-193, and I don't have any references on Mossbauer of it, and I'm not, I think it's been done, but I don't really know offhand. We haven't gotten any beam time yet. I'm hoping maybe Kai can put in a good word for us with the, being very powerful and important person that I can tell he is. So anyway, these are not related to anti-cancer. You can just see the small picture here, but these are also coordination compounds, and they're related to light-emitting devices, which you can see these beautiful colors that I got from Tom's website showing, by making small changes, you're addressing different emission properties. And so we're hoping with Mossbauer we can connect electronic structure to the light emission properties as well. So that's I'm pretty sure the last slide I want to have, and thanks for your time.
Thank you very much. So it's time for questions. So very interesting talk about osmium-based drugs. So let's continue with questions. Someone in the audience? Zamora, please. The microphone is nearer.
You showed different Mossbauer spectra. They are quadrupole spectra. They show some asymmetry. Do you know where does this asymmetry come from?
No, that's the short answer. We haven't really analyzed this enough. I don't know. I mean, these...
Is it a problem of preferential orientation?
Yeah,
Because
it's possible. I mean, these are, we're probably at about the minimum amount of material that, I mean, with, say, iron compounds, we would be unlimited, but we had a small amount of enriched, of the osmium isotope and tried to divide it up. So whether the sample size is a problem, I mean, it was enough, but I just don't know whether that's a factor. I can certainly say that there was, we were, in preparing the sample, which I couldn't be there, they sort of were pushing the envelope in terms of having enough material there, and how that's reflected in the Mossbauer spectrum, I don't know.
Another explanation could be to have two components.
Yeah, that could
is it
be.
possible?
This is the one, the oxide.
The few ones.
Yeah. Yeah, I don't know if there's, let's see, I don't remember from the crystal structure whether there's more than, there could be, I just don't remember that crystal structure. But yeah, that one wasn't, as I said, it wasn't one that I personally was that interested in, but they sort of seemed that was the most feasible one to try and get something out, but
And in the case of the experiments with synchrotron, did you find also this asymmetry?
Yeah, let's, we go back here.
You have both. Yeah.
Yeah. Right, so you're talking about.
Because this Mossbauer spectra was built from the synchrotron time spectrum. Okay.
Yeah, I don't,
Thank you,
I don't have any pictures for comparison. I mean, the problem too with the old data.
Now,
the first, I didn't show anything from the paper where they had the metal, and then of course the Wagner work was osmium 189, so that's a whole different story. Obviously, that's what I thought. Oh, that's what we should do, and it's a higher abundance. But for synchrotron reasons that I have no idea about, this is what they say. No, Demetrius says no. We have to have 187, and maybe somebody can explain to me why that is. It's like, okay, well, that's what it is. It has the advantage that we're hoping also for NMR, because it is a spin 1/2. Although I haven't been able to find anybody wanting to do solid state NMR on these systems once the Mossbauer is done, but in theory that would be of interest too. But yeah, it's still pretty early on in the whole story.
So one more question, please. Edson, you have some remarks from lunch?
Yeah. So
thank you very much, Dr. Telser.
Yeah, sorry.
Telser.
Boa tarde a todos. Good afternoon. Welcome back to the afternoon session. My name is Marlon, and I'm going to be the chair of this session. Now we're going to have a lecture by Ligia Zamora from Universidad del Valle, Colombia, and the title, the presentation is Mossbauer Spectroscopy Applied to the Study of Permanent Magnets. Please.
Thank you. Good afternoon, everyone. Thank you for the invitation to start a presentation this word. It's okay, listening okay, okay. Is Mossbauer spectroscopy applied to the study of permanent magnets? Sometimes I talk about PM, but it's permanent magnets. The magnetic field is, the talk is divided into parts. One part of generators of permanent magnets, and the next one is a presentation of our results in Colombia, but specific Mossbauer results. So magnetic field for technical applications are obtained in two ways. One way is for electromagnets, and the other way is from permanent magnets. The idea of the permanent magnet is better because they don't need electricity to obtain the fields obtained. Yeah. So, what is the motivation to study permanent magnets? Because many electronic devices or many electronics in our lives use PMs. for example, in computers are parts of them that use PM. Also in the car, there are many places into the car that use permanent magnets. Also in hard disks or medical device or home electronics. So it's many situation, many device that we use permanent magnets. The idea when we talk about the PM is because we think it's a source of clear energy. But it's necessary to have the idea, for example, wind turbines is clean energy, and they use 1 amount of neodymium iron boron that is a permanent, is the king of permanent magnets. Also into the hybrid electric cars also use a lot of parts of PM, different parts of EN, amount of neodymium, iron, dysprosium boron are necessary to use in that car. But the problem is this analysis in 2011, 2012, but now is similar, or maybe now is wrong that in that years. Yeah? There are mines or air art are specific. The mark production are produced in China. But China is the most producer of this rare earth, and they increase the price of rare earth because they want, they could. So this problem, the idea is we to put another elements, difference, to change this power of the China with the price increases about the elements rare earth. Now it's only two years, but now the problem is similar, is equal, no change with the years. Also, China say that they have mines only for 20 years more. So in few years, the mines disappear, and what happened with the PMs? What happened? So I put this hysteresis loops, but I don't know that you know the hysteresis loops, but only I need do you remember some of the hysteresis loops for permanent magnets. The hysteresis loop, I need that you remember what is saturation, which is one that all spins are aligned with the applied field. When we decrease the applied field, there are a point when the high applied field is 0, but they have one magnetization is no remanence. And also when we decrease in the other way, increase in the other way, there are points when the magnetization is 0, but when necessary a coercive field applied in the other direction, that is coercitivity. For us, for permanent magnets, is important saturation, remanence, and coercitivity. This is only for to have in mind. Characterize permanent magnets is necessary. I return to hysteresis loops. It's necessary to concentrate in the second quadrant, this loop, this place. So if we have possibility to obtain magnetization versus field field or magnetic fluid density. The product, we have this curve, and for each point we have one B and one H, and the product B by IH is known energy product. It is the most important value to obtain or to work in permanent magnets. What is the idea? the idea is in the second quadrant for each point to make this product for B versus H by H, B by H, all points, obtain this curve, the B versus BH product, energy product, and the maximum value, which expansion is the best obtaining for obtain the information about the permanent magnet. So, isn't always when we work with permanent magnets, we need to make hysteresis loops and we need to make this curve. Yes, it's necessary to characterize very well the permanent magnets. So the permanent magnet must have high spontaneous magnetization, high remanence is another requisite is necessary, high coercitivity file, anisotropy high also with a constant of anisotropy high, and high cure temperature, better, bigger than room temperature. So this demanded that all PM have these values. Manufacturing PM is necessary to study intrinsic properties like magnetization saturation, anisotropy constant, but is units microstructure, for example, reduce the size, yes, for obtained the extrinsic properties and the extrinsic properties like fine remanence for obtain the biggest product, this one. This is the manufacturing to obtain the best of them. This idea of the value for permanent magnets, neodymium iron boron is in this moment is the king of the PM. They have a theoretical simulation. They write these values of BH. Experimental up now, more or less, this is the value of BH. Different values, different compounds are for PM. In this figure, we have what is the change of the different compounds with the years. In this way, we can see how with the years decrease the size of the PM. The first one was steels, is longer, is need to produce fields, high fields. Ferritas, alnicos, okay, but is decreasing. Neodymium iron boron is necessary for few size to obtain the same results. So and here we can see the product BH maximum in this way. Also, the steel has in these years low values will appear another compounds, these values increase, and now the king, I'll say, is neodymium iron boron. He has values of 50 and 60 more or less in this value. What is the idea in the work is to find new magnets. What is the idea? To find new anisotropic compounds, possibly with less air content. Is looking for one investigation, but it's difficult. It's difficult to get. The second one, define new anisotropic compounds, possibility with less air, but it's no obtained yet. And there's a new concept, no rare earth magnetics, due to 97% of rare earth mines are in China. That is the idea. Fabrication of magnetics with large remanencia, with large coercitive field, with large car, to change microstructure, for example, annealing, reduce grain size, are the idea to fabricate PM. Another form to prepare nanocomposite magnets is mix exchange coupled, is the name, exchange spring magnetic, when we unit soft and hard phase. For example, here is hard hysteresis loop, here is soft hysteresis hull. The idea is mix together for obtain this one with high magnetization saturation and high coercitive field. That is the idea, the words with exchange spring magnetic. For example, this simulation more or less what can see. This is only hard phase. This is approximately one value, what we can see. And if we put isotropic in only one way, more or less, only hard phase, we increase the product VH maximum. If we put iron, this, for example, neodymium hierro boro is the blue, iron is the yellow, neodymium iron boro is hard, iron is soft, but when we put an isotropic coupled between them, is increasing more or less after this value. So it is the idea, there are new forms to prepare this permanent magnets. Remarks, the permanent magnets are used in many applications. Repeat, saturation, constant, cure temperature increase. New stranger magnets are necessary, and because rare are in limited supply and are critical materials. Now I will show you what is our results in Universidad del Valle. The Universidad del Valle, we have some studies that we use Mossbauer spectroscopy, but the other ones no. For example, we have manganese aluminum carbon is another is permanent magnet, is PM, but it's impossible to study by Mossbauer because we know we have a source of iron. But the first word we start by neodymium iron boro. We take elements to commercial neodymium iron boro, and we change the particle size. What is the product BH maximum? We change the size. Another studies was neodymium hierro nickel boro to change maybe hierro by nickel, maybe hierro by cobalt. Maybe the idea is possible to increase the BH maximum. For exchange coupling manganese aluminum carbon is the hard with iron alpha, is nanocomposites. And another one is that we know, like 112 is permanent PM also, and iron 13 change the Indian vancilism. I will show only one. This results in Mossbauer this is one, this is one, and this is one. Results obtained in our university from different students and magister student or doctoral student. So in this moment, we are studying what happened with manganese aluminum carbon band in thin film fabrication. Is up now was difficult. And the other is another one, 112, like this. The idea is decrease the content of RR for use less RR for obtain the same properties. Okay. And now I don't show you about the X-ray diffractions. All system force fields always are studied for X-ray diffraction, but I don't show here. I don't show only Mossbauer and the product BH maximum. So this is neodymium iron boron. Commercial powders was we bought neodymium iron boron, was separated in 5 different steps, and after that was milling. Is looking for a study what is the behavior when we change the particle size. Yes, so this is a structural of neodymium iron boron. Is tetragonal. This is the idea of how is the structural. If you can see, we have green is the points, the sides of boron. Neodymium has 2 seeds, are the red ones and the yellow ones. Each seeds are denoted by F and G. And the iron is the other one colors, has 6, 1, 2, 3, 4, 5, 6 no equivalent crystallographic size. So this study was made also with X-ray dust, obtaining the phase that we need, but by Mossbauer, but was fitting with this idea. The fitting is 6 sextets for the 6 iron seeds, 1 sextet for the phase neodymium iron boron, and 1 doublet for another phase neodymium iron boron, but neodymium not 240 base, 1.1 for iron 4, boron 4. This is the fit. This fit is in agree with the X-ray results. The important with this fit, or the students made the fit, this is important to obtain this situation. The high file, each place has this decrease in this order. In other way, pues, it's necessary to make the hysteresis loops to obtain the BH maximum, and the BH maximum was obtained, the bigger was for 60 micrometers, one of civil samples. So we can conclusion, reduction of the particle size by mechanical alloying is not favorable because it introduced defects into the sample, degrading the magnetic behavior. The idea is that maybe milling, decreasing the size, should be increase the values of BH, but no, there are a limit, and the limit is this value for this size. Exactly. Other word was iron 3 tin. Iron 3 tin was proposed because they have good properties, but first the proposal was theoretical, and we tried to realize experimental to obtain that the theoretical proposed. We tried, but was no easy. What happened with iron 13 has good properties that the 1 PM is necessary to obtain a 1 excellent PM. But what is the problem with iron 13 is only stable, is a stabilization in these parts. So it's very difficult to prepare this sample. It's necessary prepare this sample only by solid state reactions. Is the only way. We try different ways, but only with one student realized 1 year to try to obtain iron 13, but was only after many work we can obtain the pure phase. Is the first step, but it's difficult to step. So this is here magnetization. But if you do the hysteresis loop, it's very soft. It's soft, no hard magnetic. That the idea is to increase this key, this constante, anisotropic constants, maybe change, in the first proposal was chain by indium and chain by silicium. But first, this is by Mossbauer. We realize also X-ray diffraction. We obtain the phase. The same, Mossbauer led me to be in according with the X-ray diffraction. So here is iron 3 thin, is a sexte, is because is the iron and surrounded for the irons, because this is obtaining axis state. Here, for only without silicon, we obtain a little parts, another phase that is not observing an X-ray diffraction. And when we increase the silicon, was problem because the iron 3 thin decrease with increase the silicon. Similar results are obtained with indium. The substitution of tints for indium and silicon doesn't lead the formation of iron 3 thin. The doping process caused the decomposition of the iron 3 thin phase into the secondary phases rich in iron. That favors the increase of the system saturation magnetization. This means the magnetization saturation increase, but it's impossible to obtain a high coercivity bigger. No, that's the problem. The other one is manganese, aluminum, carbon. This is the BPIM, manganese, aluminum. Really, is manganese, aluminum. Carbon is used to stabilize the phase. The study was a spring exchange with iron in form normal. This is experimental. The idea is we need manganese, aluminum, carbon in the phase tau phase. The tau phase is the phase PM, is the PM. It's necessary to prepare in different parts. The first part is obtaining epsilon phase, but the epsilon phase should be promoted difference alignments to obtain the tau phase. When manganese aluminum carbon is in the tau phase, is permanent magnets. Iron, powder of alpha iron was mixed with manganese aluminum carbon. This is the fraction, the both. We create, the students was create nanocomposites of manganese aluminum carbon with alpha iron. Also, we have the X-ray diffraction, the fitted X-ray diffraction. The X-ray diffraction is in accord with Mossbauer fit. And this is the hysteresis loops. If you can see, this red one is about the manganese aluminum phase. But the manganese aluminum phase has good high coercitivity file. But the other, this one is mix of the with iron, tau phase with iron, but obtaining with different temperatures, and is obtaining that the increase the saturation magnetization is one objective to obtain in this case, but the coercitivity field decrease. But it's very important that obtain exactly the nanocomposites manganese aluminum carbon with alpha iron. Is no easy to obtain this nanocomposite. We can obtain, but the idea now is continue working with this idea, but the idea is that the coercitivity field increase. Yeah? Bueno. By Mossbauer, only because we mix manganese aluminum carbon with iron pure, by Mossbauer we obtain iron pure. No more. That is here I a few oxide obtained here, but it's the only that Mossbauer can say about that. And this is the last ones I showed you. I told you that we studied different compounds. I showed you three compounds, but we study different, and in progress now studied also different products. Are these composed? The idea is change neodymium by cerium. Cerium is cheaper. The idea is reduce the neodymium, because neodymium is costs, and the problem is a rare earth, and is property of the China's country. Is a tetragonal. The idea is this structure exhibit weak or flat uniaxial anisotropy, and if we introduce nitrogenation, improves the anisotropy. When increase the anisotropy, we wait that the properties of this PM increase also. So this system has this structural and 9112 is the name 9110. For this work, in this work, we examine the effects of neodymium by cerium substitution and of the nitrogenation in the structural and imperfect magnetic properties of this system. The study is, sorry. Sorry. This one. We pass to the sample obtained only neodymium. We have 50% the neodymium and 50% of cerium, and after that 50% of cerium. This is the fit, similar to iron, neodymium, iron boroms are different places. But the idea here is when we obtain the hyperfine files, without nitrogenation is around this value, but with nitrogenation this value increase. Here is increase division and the fit of this. This is the form of preparation of the samples to obtain this, but by Mossbauer was fitting by 7 sextets, one small quadruple components. The sextets are also of the place of the iron neighborhood. The hyperfine mean of the sextets presenta on decrease from the 28 to 26 with the substitution neodymium and cerium. But with the nitrogenation increase the hyperfine value, mean value. So we can say the cerium doesn't replace the obtained by neodymium, yes, but maybe there are other places of the use of permanent magnets where the cerium is applied. In this moment, the neodymium iron boron is the king, how you say, but it's possible to change a little or rare other for others. Is good results, but because there are in other permanent alloys, permanent magnets, where it's possible to apply the new magnets. Is clear, my dear? Okay. Okay, this is the study of this to obtain when they are anisotropic, when we put the samples parallel of field external and perpendicular field external. So the anisotropy rate increase. This is the idea for only neodymium. Here only 50% neodymium cerium. Here only cerium. The nitrogenation increase the results, is better. This obtain the nitrogenation process results in increased saturation magnetization. Yes, the best properties were found to the neodymium, hierro, cobalto, tin compounds. So to change by cerium was no excellent results, but it's good results. Because more or less está in the same values, it is possible to apply in one area of the permanent magnet. This is the last one. The before study was the choice one of them. This is doesn't have Mossbauer spectroscopy. But the idea is this system was nitrogenated, changing the time of nitrogenation, and the results here in parentheses here are our experimental results, and the values are very well for results for our results. In parentheses is randomly oriented. It means when the sample was posted in external field. Yes. So, this is the last one I want to show you. Thank you for attention. That's our collaborators in the group. This is the photo. I want to show you the photo of the group. That's our students. He is a new prophet in our group. So he is the future here in Mosbauer, Latin America. And there are Germán, there are Professor Tavares. Do you know Professor Tavares? All of them son students. All of them son students. And this is a collaboration about this in our group in Cali. With studied different compounds, not only permanent magnets, but the permanent magnet was the recent studies for us. I don't know, one more? Okay, thank you very much.
Thank you, Ligia. Any questions?
All was clear?
It's a simple question. Do you obtain a loop showing clearly the exchange spring interaction?
Yes.
Could you please? I mean, the full loop.
This one. Yes. Yes, but increase the saturation magnetizations, yes, for new ones, but decrease coercitivity fields. The idea is the increase both magnetization saturation and coercitivity force. But I repeat, that is no ideal result, but it's good result because with this, maybe this permanent magnet has application in other way of the all permanent magnets that in this moment in the obtained something.
This loop in blue is the better result you obtained? The best.
This one.
The blue one. The blue one.
Yellow or blue? This one.
No.
Blue?
Yeah.
No.
What is the best result you have had?
No, because the blue one is only this one, manganese aluminum carbon. Is the hard magnetic, is the hard phase. The other one is iron, is the soft phase. Bad mixture explained it is only the green and this one, yellow one. Yeah?
Okay.
That's okay.
You make a mixture of fraction between metallic iron and, for example, this aluminum carbon based system. So you mixture between this, hard and soft magnetic material.
Yes,
the question is, how did you prepare it? So you put this blend in the milling machine, and then not exactly that?
This sample was...
How did you prepare the composite?
The composite.
Yeah, how did you prepare it? So you got the iron powder, and then you make a blend of them.
Maybe it was this one prepared by milling, cryogenic milling.
Yeah, that's the point. So you mill the machine, you have milled the machine for 4 hours.
Yes.
In nitrogen atmosphere.
Yes.
That's it, in nitrogen atmosphere. So the question is, you don't have interdiffusion between the iron and your hard magnet? And also, according to the question of Andrea, if you look to the magnetization, if you put any kind of magnetic, so what is going to have, you have to increase the saturation, because as your introduction, you have shown that soft magnetic phase, they increase the remanence.
Yes.
And the hard, you increase the coercive field.
No.
So the Andrea has asked you if you have some fingerprint that you have exchange spring. So with couples, the soft and the hard magnetic phase.
Yes.
It seems that you don't have it. So the things that you have is just a normal magnetization curve, where you have a strong contribution of the soft phase. That's my feeling, because you have a strong reduction of the coercive field, but you increase the magnetization.
Yes.
This comes from probably by the iron.
Yes, it's true. Yes, it's true. It's from the iron. The yes, it's from the iron. But also the proportions of the volumetric fraction of the hard and soft are 80% for hard, 20% soft. There are no more soft is no good for experience exchange. Yes.
Another point is also, what about the size of the grains? Because
micrometers is more or less.
For both of them? Micrometer?
Yes.
But for both of them?
Yes. I don't know the iron. No, I think there are less of
because
the iron.
If you produced first by milling, so it's as I will again comment this, if it is not micro particle, it's a micro nanostructured particle. So it's difficult to have a real, how to say, exchange spring magnet. And the size is very important to control for both soft and hard.
Yes.
Did you test some heat treatment? Did you test some heat treatment after you performed the milling? Did you test it?
For separate?
No, my question, after you prepare your sample.
After,
you have your sample, which is a composite of soft iron plus your hard magnetic. So you mill this blend. After you mill this blend, did you perform some heat treatment? So you put in the oven and keep there for, I don't know, 2 hours, 24 hours in some temperature to see if you can reduce the defect or stuff like that? Do you understand my question?
Yes, I understand, but I don't know.
If you did it. Okay.
Yes, I don't know if they did it exactly. What is the size after that?
Okay.
After that, I don't.
Okay, you have
I
to
don't
think
have
about.
I don't know if Herman know. You know the response of that? No, I don't know. But manganese, aluminum, carbon, like iron, neodymium, boron, reduce the tamaño of them is very, very difficult because are, I don't know how to say, magnetic elements difficult to reduce the size of them. That's Janmar.
And did you try to do the milling at room temperature and after to compare with cryogenic milling?
Sorry, again, please.
Because you produce with cryogenic milling during 4 hours.
Yes.
And did you try at room temperature the milling to compare the two composites if they differ? No,
I
yes.
don't know. See, this is. No, only cries this temperature. No.
No, because the idea is why to do cryogenic milling. Is it useful?
Why?
Yeah.
To obtain the idea is to obtain the strange sprint.
But what will be the effect of temperature during milling?
I don't know, because we tried different forms. Also milling with normal room temperature, but we don't obtain the string. When we do the hysteresis loop, we obtain the separate the step. We separate the no continuous lines. Do you know?
Mm.
Yes, at room temperature. So only to do that, we obtain the continuous obtain to strain sprint.
So finally, because of the mechanical properties, you are breaking finally the grains.
With temperature?
The small blocks.
Yes.
Because of the temperature.
Yes. I think so. Yes, that's the idea.
Thank you, Ligia, for your nice talk.
Thank you.
I would like to know regarding your Mossbauer spectra, if you imposed any constraints on the hyperfine parameters, because I see that you use a lot of sites.
Yes.
I don't say like crystalline sites.
Yes.
And I mean, if you do that, you may have to know very well your structure, which I think is the case. But
yes.
I wanted to know, how did you dealt with this problem, because it is a problem.
But also we realize X-ray diffractions.
Yeah. But how? I mean, did you know the hyperfine parameters for each of those sites for the iron, or did you impose any constraint, or it's just a curiosity if you fix the parameters, or for example the isomer shifts were equal between the iron sites?
Okay, this one.
Yeah, in general, because okay, that's for the hyperfine field, but what about the quadruple interaction and the isomer shifts? Were they different between these iron sites, or?
I don't know that we realized, but I don't hold this. I don't have the question now here, but well, we made this relation. We compare it with isomer cheese, all of them. For each site, we made the graphicals.
Okay.
But I don't know in the moment how to say.
Because I am used to such a spectra, so probably what you have done is to have a constraint on width of lines. To consider, for example, for one site, I do not remember, 16K2 and 16K1, to consider the same line width. Because here we can see that probably there is much more than 6 sites because of grain boundaries. Again.
Yes.
And in the last series, because you introduce titanium, cerium, and so on, so you will multiply the number of neighbors. So you have a lot of components. And of course, you can admit that if you consider the same line width for different sites, why not? I would say. I don't know
okay,
if you are right.
You. Yes.
Any question? So let's thank again to Ligia.
Thank you.